Okay, then without further delay, so Unit 1 is the fundamentals of electricity. Like I was saying, kind of a science experiment. Definitely not something that seems like it's going to help you fix the car, but like I explained, you get these weird vehicles, you're not sure what to do with it. You can resort back to knowing how electricity works, right? And so if I've got a bulb that's dim, I can apply my understanding of electricity to say if my bulb is dim, there must be excessive resistance in the circuit that's leading to a voltage drop that shouldn't be there, and that therefore would make the bulb dim, right? So if you understand really the theory and the concepts, you can apply that to do the diagnosis. So this is going to be some foundational information. All right, so first justification. I recommend that people study electrical first, and the reason why is it applies to pretty much all the other areas of the vehicle. So if anybody in here says that they want to just be, anybody want to get into like doing smog testing, anybody want to be a smog tech, they can make good money. If you want to do smog, a big part of that is electrical. How about anybody for transmission building? Nobody wants to be a transmission builder. That's not really. You want to be a transmission builder? Cool. That's got a lot of electrical in it too. How about, let's think of something else. Oh, you just want to do brakes. All you want to do is put brakes on the car. Well, that sounds good. You could put the pads on there. That's not electrical. But ABS, you guys ever heard of it? Anti-lock braking systems, all electrical, right? So what we're going to cover is kind of specifically tied to a particular ASE called ASE A6, electrical-electronic systems, but this is going to bleed into all the other areas, all of them. There's really no exception. Even let's say, who's interested in self-driving cars? Now you want to drive your own car, but do you want to get paid or not? Other people want the car to drive itself. They need someone to figure out those problems, diagnose, repair those cars, right? So if you want to drive a 1967 Camaro, cool. You need money to pay for that. So I would work on the new self-driving car and take that money and buy the 1967 Camaro. You see, that's how that works. So just keep this in mind. It's going to be necessary for all the subjects. All right, so let's go over some of the principles and some of the basic things. When we get into repairing the vehicle, a lot of this is going to have to do with electrical, electronics, computerization. It's going to be very electrical heavy on a modern vehicle. So if you don't like electrical, your options are do something really basic like a lot of oil changes. You could do that and not know electrical. Or you can try to specialize in classic cars, which classic cars are cool. If you really wanted, you could do, you could be like a carburetor tuner. You could tune carburetors, but the problem is there's less and less of those types of jobs, right? So if the car's maybe like 1970s, there's pretty minimal electrical. But if the car's 80s, there's more electrical, 90s, more electrical, 2000s, more, 2010, very electrical based, 2020, extremely. So you see the trend, right? So a lot of people see electrical and they're like, nah, I don't really want to do that. I'm sorry, it's going to be unavoidable. Cool. And especially with the cars coming up, right? So you guys know hybrid and EV, you're excited about those? Okay, well what if I tried to get you more excited about hybrid EV? Let's say, all right, who's into pickup trucks? All right. No, anybody like a Tundra, Toyota Tundra, gas Toyota Tundra? Yeah, the highest performance Tundra is a hybrid. So you're like, wait a minute, I thought hybrid was for just like efficiency. I'm saying, no, not really. What about Jeep Wrangler? I know there's some people, I saw it. You just don't want to say it in front of your friends because it's a Dodge, it's a Fiat. Like a fix it again, Tony, you know what I'm saying? Okay, if you have two options when you buy Wrangler. You can get the V6, you think that'd be higher performance, or you can get the 4-cylinder turbo, that's actually the higher performing model, and it comes with this e-torque, it's like a belt alternator starter. It's technically hybrid. So see, you thought hybrids were Priuses, and they are, but also the higher performance Tundra TRD or the higher end Jeep Wrangler Rubicon with the turbo 4-cylinder is a hybrid as well. So if you want performance, a good way to add performance to the vehicle is to add electric motors to help the engine. Or let's say it's the new Corvette. They have a new Corvette. I think it's something X, ZRX or something. Do you guys know that one? Not the ZR1, but there's the ZR1. That one's its own animal. But there's an all-wheel drive one. Is it the ZR1? The ZR1 comes all-wheel drive now? I'm not 100% sure on that. We'd have to look it up. But there's a new, I'm going to look it up right now, just because it's bothering me. There's a new Corvette. I saw it. I know it's called the X. ZR1. It is called the ZR1X. Okay. So the top of the line Corvette, where you got the base model, that'd be like just the Corvette, the Stingray. Then you got like the Z06. Oh, now we're talking. Then you got the ZR1. You got the ZR1X. The ZR1 is very high performance, twin turbo, 640 naturally aspirated horsepower. Or the Z06 I think is naturally aspirated now. But let's see, Z06 NA. Yeah. They go up in levels, right? So you got naturally aspirated, pretty big power that they're making now on the Z06. ZR1 twin turbo, ZR1X twin turbo, gas, cool. But then they add electric motors to the front to drive the front wheels. So now you have a Corvette that's all-wheel drive. So you thought, the Corvette, you can't drive that in Big Bear, Idlewild or something. You get the ZR1X, now you can. So the way that we used to add all-wheel drive was we'd have to have like a transfer case and a drive shaft and a differential and all that stuff. It's actually kind of complicated to do that because you're going to have to build a tunnel for the drive shaft under the car and rework the body. Now they're like, you know what? We'll just put an electric motor in the front and put some axles. You don't have to have a drive shaft. You can just have a computer and a bigger battery, and the bigger battery using an inverter can actually power the front wheels, right? So like electrification of the cars is not just hybrid stuff like Prius. They're doing a lot of performance things with electrification too. So again, if you want to work on the newer cars, you need electrical. If you want to work on the really high performance cars, you need electrical. If you want to work on cars that are 20 years old, you need electrical. So there's just extensive reasons why you need to really know this. And then understand as well the daily tasks for a technician now. They're different than what they used to be. So like when I was a kid, when I would walk into a shop, there'd be a mechanic. They really went by the term mechanic, right? And they'd be there looking kind of greasy and just like they've been into some projects, and there's grease all over here and on the face and everywhere, and it'd be like, oh yeah, you want me to work on your car? And they'll just do mechanical things. Like I remember as a kid, they would just do stuff like change brake shoes for drums. They'd be changing shoes and doing this, very mechanical. And there's still a little bit of that, but your typical problem back then would be, maybe the car's got a loss of power, and they'd be doing some tune-up stuff, replacing electrical parts, but not necessarily really diagnosing. Whereas now, if you get that type of problem, we're very quickly looking to electrical, right? Checking codes with a scan tool, looking at wiring diagrams. A lot of times if a code sets it's an electrical fault, sometimes it's mechanical, but like that Tahoe I told you about, it's got 15 different diagnostic trouble codes that set intermittently once every 2 weeks. That's going to be an electrical concern. So a lot of times what I do is zoom out and be like, look at the wiring diagram and see what do all these sensors have in common. Do they all share the same wire? Do they all share the same ground? Do they all share the same connector? Right? They're going to have something in common, so it's very normal for a technician today. You notice I changed from mechanic to technician. It's very normal for a technician today to be into wiring diagrams, doing electrical diagnosis every single day, like for a big portion of the day. It's just the way it is. So now you can even say mechanic versus technician. Pretty big subject of debate. For me, don't really care. I don't. You could. I'd refer to either one as myself as either one of those. Neither one of them bother me. But if I had to sum it up for you in the way that makes the most sense, mechanics back in the day were mechanical. You had loose parts, you had worn parts, you had things that needed to be disassembled and cleaned up and greased and reassembled, right? It was very mechanical. So if you hear someone has good mechanical ability, good mechanical inclination, you'd expect, like, if you bought a bicycle and you just threw the parts on the table, you know they could probably figure out how to put it together, right? That was really like mechanical. That was like what a mechanic did. And it's not just automotive, by the way. So if you're into heating, ventilation, air conditioning, they have HVAC mechanics too, and they're dealing with, ducting and fabrication, nuts and bolts, and working with metal. They call that an HVAC mechanic. So you're kind of like for me when I was younger, I saw a job posting and it said something about mechanic, and I was like, hey, that's a job. And then when I called them, they're like, well, this is an HVAC mechanic. And I'm like, what's a mechanic? So what is it, fixing the HVAC trucks? Like you have a fleet of vans or what? It's like, no, this means like it's a specific job. So mechanic isn't just on cars. That could mean a lot of things. There's obviously diesel mechanic too. So it just means someone who's nuts and bolts. Even on assembly lines, they'll have mechanics that may repair the machines and stuff like that. So if you look at technician, more what that means today is that's someone who's very specifically trained to work on the modern vehicle. So a mechanic would work nuts and bolts. A technician, you bring in the car and you say, like, here's the customer concern, and they should be able to do mechanical things, yes, but a lot of what we're doing is troubleshooting, and it has mostly the addition of electrical to blame, right? So if it's a new car with a problem, you're talking about it's computer controlled, it's very electrical. Your mechanical ability doesn't help you with that, you understand? Back in the day, it used to. Like, if you could do nuts and bolts and do puzzles and take things apart and put them back together, you'd probably be pretty good in this field. Now be honest. Anybody who you talked with a counselor and you decided to do auto, did they ask you this question? Do you like to work with your hands? You like to work with your hands? You should be a mechanic. You can work with your hands. And then just be honest with yourself. Think about this. If you think of a 2020 vehicle, and it's got, first off, why are you even bringing it to the shop? Like, if you had a 2020 or newer, some of you got some pretty new stuff, why would you even bring it into the shop? Give me an imaginary customer concern. Anything? Check engine light's pretty common. How about it won't start? How about the power steering doesn't work? Airbag light is on. Everything we just listed right there, not likely to be mechanical. So if you just think of the modern vehicle, it's so electrified and so computerized. Maybe one thing that'd be mechanical, you're driving down the road and it shakes while you're driving. Like, that would probably be more mechanical. You might pull the wheel off and inspect it and put it on the balancer and measure the balance and see if you see maybe they hit a pothole and it bent the wheel, right? You could spin it, you could see the wheel do a little bit of this. Like, mechanical aptitude is still valuable, don't get me wrong, but most of the time cars comes in, it's for a customer concern, and you're not just using your hands, you're not just working with your hands. Like, the cars don't come in and they're just like, yeah, I just want you to, like, take my wheel bearings apart and re-grease them and then put them back together and pack them and then set the bearing preload. Like, that's not what the job is anymore. Those days are gone. Now it's more like I have a noise, or I have the noise could be mechanical, but now it'd more be like I've got an ABS light, and then you perform your troubleshooting and inspection, and you actually find the wheel bearings loose, and you replace the wheel bearings. So you're marrying the electrical and the diagnosis with the mechanical of finding a loose bearing, right? So to me, that's the difference between mechanic and technician. Mechanic would do the mechanical things, not so much troubleshooting. A technician now, they're trained for specific, we're specifically trained to work on these vehicles. So if you have excellent mechanical aptitude, I can't throw you on a 2026 vehicle right now and expect you to be able to fix it. Not going to happen. You don't know. You have to know all about the system, and without specific technical training, you don't know. Make sense? Like, you just don't know. So that's why it's a technician. The technicians are specifically trained to work on that type of vehicle. Right? To be honest, if you gave me like some of these guys, like Ron and stuff, they like these old hot rod cars, like a 1950 something. I don't really know what to do with that. Maybe embarrassing to tell you, I'm just letting you know. Like if a 50-something car rolled in, you'd see Bob, but Bob probably be pretty good at it. Bob be like, oh yeah, you adjust it like this, and you turn this screw for that, and you adjust this thing for this, and I'd be like, I don't freaking know what to do with that. I have no idea. I was really specifically trained to work on the 2000-something and up vehicles. I got no training on the 1990s. I just, hopefully that clarifies the difference. All right, cool. So as we get more into the system, you'll notice electrodes and bleed into everything, like we were saying. Electrical aspects control a lot of things. So remember I mentioned, maybe it's got the power steering doesn't work on a new car, right? If it was an old car and the power steering didn't work, we'd be out there checking the fluid, being like, oh, it's got power steering fluid in it. On a new car, you know the power steering's electronic. So, like, what do you do? What would you even do with that? It's hard to even say what the heck you would do. You'd have to think about, oh, how do I look at the electron level? You can't see that. So if it's an electronic power steering car and the power steering's an op, you're probably going to start with checking for codes. You're probably pretty quickly going to get into electrical wiring diagram. You're probably pretty quickly going to start checking for where there's voltage, where there's supposed to be, and if there's voltage missing at some part, right? So boom, instantly your power steering concern went from checking fluid level and looking for leaks to codes and meter use and wiring diagrams. Boom, just like that. So electrical, EPS we'll call it, electronic power steering, mostly became prevalent in like 2010, maybe 2006, but if something's like a 2014, it's probably got electric power steering. It's just the way it is. Right, so it's just different. And kind of the point of that is we can take electricity and have it do work for us. So that's the main reason we have this. So electric power steering is an example. We used to need a pump, and the pump would be driven by the belt, and the belt would be driven by the engine. It would turn the pump, and the pump would make pressure, and that way it could help us steer the car, right? So we were using mechanical rotation to turn a pump to pump fluid to help us. Now we're kind of like, you know what? Those systems, the pumps tend to wear out, the hoses tend to leak, the belt tends to squeak, and also when you're driving down the freeway, you don't really need power steering because you're not really steering. And if you are steering, you're going so fast it's really easy to steer. So like on an older system with regular power steering, you're going down the highway and you're just turning the pump and you're wasting gas. Make sense? And you're also increasing your emissions. So on a newer car, they're like, you know what? Let's get rid of that old mechanical power steering. Let's junk the hydraulic power steering. Let's put on electronic power steering. So if it's electronic power steering, why is that an improvement for fuel economy and emissions? My question for you. Why would that be better?
You're moving into the overall motion.
Kind of. So like if we're at low speeds, we can have it work really hard, and it's going to pull electricity from the battery, and the battery is a big storage box, right? So if the alternator charges the battery, which it does, it might not be able to totally keep up with your power steering like on maximum use, but that's okay because the battery stores a little extra electricity. So we can take our electronic power steering and like maybe not have to make it super strong because we have a battery there that's going to provide some extra buffering, if you will. But then when we get on the freeway, we don't need power steering anymore. Shut the electronic power steering off. It's just disabled. So you're no longer sucking power. Like if it was mechanical belt driven, you can't just like take the belt off and put the belt back on, right? It's constantly draining and drawing. Whereas if it's electronic power steering, computer controlled, it can look at your vehicle speed and be like, oh, we're at 70 miles an hour. we need no electronic power steering, do no power draw, no loss of fuel, no increased emissions, right? So there's some benefits there, and that tends to be the driving force in the vehicle. So the part of the reason it goes more electrical, one of the factors is better for fuel economy, better for emissions, right? Mechanical things are, they're older, but they're also, they were never made with efficiency in mind, right? They didn't put power steering on a car to think, oh, let's get the fuel economy up. In 1955, when they added power steering to the car, they didn't care about fuel economy. Gas was basically free. So they're like, just add more stuff on there. We don't care about the gas, make it comfortable. Now we're sort of like, we need to save gas, so mechanical things are quickly being outdated. The other thing is, as we move towards self-driving and advanced driver assist, think about these things. You want the car to be able to steer itself, right? Good luck doing that with a power steering pump. Power steering pumps have no intelligence. They just pump. That's all they do. Whereas if it's electronic power steering, we can actually use the computer, because computers work well with electronics. Make sense? Electronics work well with electrical systems like electronic power steering. So we can have a computer communicate with the EPS and tell the EPS, hey, you know what, we want to steer a little to the left to keep it in our lane. A lot of cars that are not even hybrid, just regular gas cars have, they'll have some sort of lane keep assist, or, like blind spot monitoring and these types of things. They can actually give you some corrective steering without you even touching the steering wheel. Cool. So electrical things are better for efficiency, but they're also better, kind of like, I'll say loosely, for safety. Really the best thing for safety is you paying attention when you drive, but good luck getting all the customers to do that. They're not going to do that. So we implement a system where it's like, hey, if you start to drift out of your lane, it'll correct itself, right? So the more we can computerize it, we can automate it, we're getting closer and closer to the car driving itself. We're getting safer and safer if the customer's on their social media while they're driving. Okay, it kind of makes sense. It's just the way that it is right now. You could be like, oh, it shouldn't be that way. But I don't really particularly care about Hollywood, to be honest. But I just recently read a thing that the way they're making movies now, they're restating the plot up to 5 times to account for the fact that they know people are distracted on their phone while they're watching the movie. That's where we're at. People's attention span's so short, and they're so unable to pay attention, they're remaking the movies so they restate the thing 5 times in 5 different ways to be sure that the people watching the movie actually know what's happening. Right? So if Hollywood's going to redo that, do you really think the automotive manufacturer is going to be like, you don't need lane keep assist, pay attention? No. They're just going to be like, yeah, we'll give you lane keep assist because we know you're on your phone while we're driving. We just know it. That's why we restated the plot 5 times in the movie. I'm just saying. All right, now let's talk about what electricity can do. We know it can do power steering, right? But there's more. You want to be able to see at nighttime, right? Electricity can make light. You want to be warm? We turn the heat up in here. Electricity can make heat. And then when we talked about electronic power steering, if you think about it, somehow electricity is making that thing work, but the way it actually does it is, we'll just say magnetism. Electromagnetic induction is where we can use electricity to control magnetic field, and the magnetic field can make things move. Okay, makes sense? So we can make light. Light and heat kind of go together, by the way. The whole reason when you turn on your headlights, if they're old school lights, the whole reason they make light is because we're getting that little filament inside really hot. But we're not getting the filament hot to warm our hands. We're getting the filament hot to make light. Make sense? And so we're using electricity for various different things. So like if you see, we could do attracting and repelling forces cause the particles to move and perform work. That's when we're getting into the electrical theory. Cool. So that's what we'll get into here. All right, pretty fun. Okay, this thing got mad at me. I think I was playing around with it too much. Here we go. Okay, this is, has anybody seen this before? Now here's where it gets to be a science class. So you guys know that's an atom, right? So when we talk about matter, all things are made up of these atoms. So if you look at this, you guys can see a little proton right there, right where this, I'm gonna have this mouse right here. Boom, proton, neutron. And then you guys know, mainly with electrical, we're mostly focused on the electrons. So when we start talking about the electrons, you just need to visualize this. The electrons are the little particles that are going around in orbit, basically. So when we get into what's a good conductor and what's an insulator, it actually all has to do with these electrons. Cool. So quite literally, when we have electrical flow, so let's say you turn your headlights on, there are going to be electrons actually traveling through the wire, and they're going to go to the light bulb, and they're going to go through the filament, and then they're going to be, you'd say, like, used up. And somebody asked me this question, and truthfully, I don't totally grasp it well enough to explain this. All right, so I understand electricity as a technician and through an automotive lens. But this person asked me, when these electrons go through the filament, do they do they come out or they bleed off or something? I know the answer is no. These electrons will leave we're gonna say positive and negative. Okay, there's a strong argument, and I think it's correct, that it's technically negative side of the battery to the positive. That's conventional versus electron theory. Electron is negative to positive. Conventional is positive and negative. In this class, we're going to focus on positive to negative because that's really how the wiring diagrams are drawn. All right, but just technically, if you want to really geek out, you could be like, let me understand electron theory, and you'll realize it may be flowing backwards, and then you're going to be really like confused, and then you come back and you can teach me. But for now, let's just say conventional, positive and negative. They leave the positive battery terminal, and they all go to the negative, right? They don't disappear. So when it goes through the bulb, the electron's not flying out, right? That was this person's question. Is the electron flying out and making light? And the answer is no. The electron goes through and it contains energy, and when it goes through, it's giving off energy, right? So then you get into like physics, you know, energy can't be created or destroyed. It really just like changes state, transfers, right? So there was electrical energy in the electron. Now the electron has less energy, and it expelled its energy in the form of heat, light. Okay, so it's kind of weird, but these electrons literally will go through the actual wire. Okay, and generally we're going to talk about beginning at the battery. So now that we've established that, just keep in mind, each ring or shell can contain a specific maximum number of electrons. So this is like, you know, periodic table of elements type of thing. Every single element can contain a certain number, will contain a certain number of electrons. And what's a good conductor or insulator all has to do with that right there. Okay, if you have equal number of protons and electrons, the charges within the atom cancel each other out, so it has no charge. All right. But what if an atom has more electrons than protons? That's going to make it have what type of charge? Negative. Interesting. So that sounds negative. But it sounds like it's kind of motivational. Do you see how something had no overall charge would be kind of like it's not motivated to do anything? It's not really charged up, right? Whereas you have something with a negative charge, that's kind of interesting. That sounds like I don't know everything about, you know, nature and physics, but typically when something sounds more balanced, you think it's going to be like a little more comfortable where it's at, right? So if you had, let's say, a tire, right? And let's say right here, this is 0 gauge pressure outside, and you had 0 psi in the tire, and you stabbed a hole in the tire, what would happen to the air? The tire's got 0 and the outside air has 0. Nothing. What if the tire had 30 psi and the outside air had 0 and you stabbed it? What's going to happen? The air is going to try to come out, right? So like just understanding in nature, things tend to try to equalize. You ever notice that? All right, how about this? What if in this room it was 70, and what if in the shop behind us it was 32 degrees. This 70 is going to try to work its way into the 32. You know that, right? Whereas if it's 70 in here and 70 out there, there's no real transfer, right? So just understanding like the way that the way that everything works in nature, things that are imbalanced, they're usually trying to switch and move and change. Okay, so that's the first thing I notice when I read this. So, like we were saying, the negative charge, the negative ion is not balanced, so it's looking for a change, right? It doesn't want to be so uneven. It wants to equalize. And that's your first thing to understand. When we have a battery, does anybody know what typical battery charge voltage is? Like if you have a fully charged automotive 12-volt battery. 12.6. Very close. Very good. All right. 12.6. That's interesting. So you have 12.6 volts of charge. That's, in automotive terms, that's a lot of motivation. It's right, like what it's saying. It's very negatively charged, so it's looking for a change. That means it's going to have like a little more electrical pressure. Makes sense? So that idea I gave you of a tire, if you had a tire, let's abandon 30 psi and let's make it 12.6 psi inside of the tire, and outside of the tire you have 0. That air really wants to come out. Makes sense? So if you go ahead and you stab the tire, there's going to be a psh. What if though the tire wasn't 12.6 psi? What if the tire was like, how about 6.3 psi? If you stabbed it, what do you think the difference would be? Slower, yeah, less pressure, exactly. So the thing that you have to understand first is with electricity, the more negatively charged, the more pressure, right? The more it's going to want to move faster, the more it's trying to get out of there. So in automotive, we deal with 12 volts. It's not that big of a deal. In this building where we plug our outlets in, that's 110 volts, 115, 120 volts. We'll call it 110, but if you actually measure, it'll probably be like 115, 118, maybe 120, right around there. So automotive is 12 volts. The house is 120 or so. That wants to get out of there more, wouldn't you say? So now do you see why we're not shocked by a 12-volt battery, but if you put your hand in the socket, anybody volunteering? You put your hand in that outlet, you're gonna feel it, aren't you? There's a lot more pressure, and it's trying to get out. It's willing to actually push through your body, because as you can see, it's a lot more negatively charged, so it's looking for a change, right? Is that kind of interesting? So it's the first concept to be able to understand. And then the electrons have the same negative charge. They repel one another. The repelling force wants to push one of the electrons away from the atom. So part of this has to do with when we have too many electrons, you know how opposites attract? And what does that mean for like likes? If opposites attract, what do likes do? They repel, they try to push. So that's what I'm saying. The more negatively charged it is, the more the electrons are trying to be pushed off of the atom. That makes sense? So the more negatively charged, the more it's looking for a change. Cool. Then if we kind of look at this, here is a negative ion atom in A. So this one's very negatively charged. You notice this? We've got 2 positives. Those are the protons. How many negative? How many electrons? 3. So this one has a lot of negative charge. This one's a negative ion. So what that would tell me is one of these electrons is kind of like, it's wanting to move on. That would be a great conductor. See how that becomes a conductor. Like when you have something that has a lot of negative charge, it's already ready to start busting those electrons loose. You think of copper. Actually, we could even look at these. Look at this conductor. Look at all those negatives. I mean, that's crazy. B is an insulator. C is a semi. So Cu I think is copper from memory. I'm actually just going to double check that for you. Here's how we do that. Cu on the periodic table of elements. Yeah, copper. That was my guess. You know why copper is a good example of a conductor? look at all that negative charge. Now we're not exactly showing the nucleus here, so I don't recall how many protons are on there. If you want, you could look it up. But anybody know what the typical wire is made out of? Yeah, now you know why. There's a reason for that, right? You know what's another few really good conductors? Aluminum's decent. Aluminum's pretty good. Copper's better. Aluminum's cheaper though, so if it's a cost savings, you know, we can go with aluminum because it's still a good conductor. And copper is expensive, so. But what else? Gold's amazing conductor. So when the economy tanks and when everything's shutting down around you and you're like prepping and all that type of stuff and you're like, what should I do with my money? Like cash has a good value unless everything really gets nasty, at which point gold has a manufacturing value, right? Gold not just for jewelry, but for electronics and electrical types of things. Gold is a really good conductor. So just, I'm not really making a plug for you to wipe out your savings account, buy gold and bury it in the backyard, but you know, there is kind of a reason why gold is pretty stable. We use it for a lot of stuff. What other conductors?
Silver.
Silver's really good too, right? So there's these types of things. Then insulators. Anybody have any guess what AR is on the periodic table? I have no idea. That's probably true. I think that's probably true. Yeah, it is. It is argon. The reason that we'll put argon on there is, like, for example, if you're doing welding or something, if you're trying to weld, you're actually gonna, let's say it's a MIG welder. We're doing a wire feed, right? And I'm gonna say positively charged, right? But this is where it gets kind of weird because you understand electron theory a little bit now, conventional versus electrical. So if we positively charge the wire coming out of the welding gun, you squeeze the trigger, it turns a little motor, and that wire starts to come out like this. But what we're also doing is we're positively charging the wire, and then that wire has a lot of electrical pressure, and when it touches the bare metal, we put a ground clamp on that. So as soon as we touch that, there's a path for electrons to flow now, and we really positively charge the wire. So many electrons flow, it'll actually melt the wire. And when you're, essentially all you're doing is a massive electrocution. It's literally, you're electrocuting through this tiny wire so much where it melts it. And the next thing you know, because it's pushing the wire out, we're shoving the wire into our weld and melting it, and it's rolling over, and we're kind of blobbing it up, and next thing you know, you're welding, and you're like, hey, I can weld. It's kind of like a hot glue gun, except it's metal coming out of there. But what we'll also do with a good welder is we'll put like a argon gas down in there. And argon's a good conductor, right? So you're not going to have any electricity flowing through the argon. That's also going to basically push the oxygen out, and it's going to keep the weld a little bit more pure. So argon's a great insulator. You know, that'd be a good one. Now, what the heck is a semiconductor? Can't make its mind up. It's like, I'm a conductor, I'm an insulator. Well, which one is it? It depends. So if we're trying to do like electronics, computerized stuff, sometimes we want things to conduct and sometimes we want them to insulate. All right, so like, for example, if we had an insulated gate bipolar transistor, it's like, what? If we send no voltage to the base, it's an insulator. But if we send voltage to the base, it's a conductor. And you're like, well, why? Who cares? Well, this is the thought. If you're trying to control electronics, you don't have time for little switches to open and close. We could use a semiconductor, and if we send voltage or don't send voltage, that'll control whether it insulates or whether it conducts. Right? So we can have millions of those in a computer chip, and they can be switched on and off really quickly. So you guys know electrical language is just on and off. That's all. It's binary. Probably kind of offensive for today. But computers are on or off. They're 1 or 0. That's it. There's no like, well, 2. Like, no, it's 0 or 1. That's it. That's all they speak. So how is it that computers are so fast if they only have 2 words, 0 or 1? Because they can switch between 0 and 1 so fast that they can relay massive amounts of information. But they have to switch really fast. So the way that we switch them really fast would be a semiconductor. they can switch on and off so fast it's really incomprehensible, and that way it can relay information, right? That's what we're doing on computers. All right, so let's say we get into there a little bit more. What if we have a deficiency of electrons? So let's say we're back on here. You see we've got 3 electrons right here, and we only have 2 protons. That would be a negative charge. But look at this one. We've got 2 protons and only 1 electron. That's what's called a positive ion, right? So when there's a deficiency, that's an overall positive charge. Well, guess what? That's not balanced either, is it? It's not balanced. It's looking for a change. So it exerts an attracting force on the electrons. It tries to pull one into its atom from another atom. All right, so if we were to look back here, this type is trying to push electrons out. This type is trying to draw electrons in. So they can both be useful to initiate movement of electrons. Remember, when we want to move electrons, there's a reason for that. We're trying to do something. We're trying to do some work. Make sense? So if you had that light bulb, if you want the light bulb to light up so you can see at night, we have to essentially motivate those electrons to go through the light bulb, right? They don't really want to go through the light bulb because there is a certain amount of resistance to go through the light bulb. It's difficult, you know. So how would we convince them to go through the light bulb? Well, we could increase the force, right? So we can positively or negatively charge the ion enough to force the movement. Does that make sense? So if we were to tie it back to the 12-volt battery, 12 volts is not really a whole lot of electrical pressure. That's like, you know, that's enough motivation to go through those light bulbs. I agree with that. But if you were to roll over to the building and it's got 120 volts, that's much more motivation. Those are much more extensively negatively charged or positively charged. So that's going to really try to push. The battery, for example, you probably won't really get much of an arc. Like if you try to go to put your battery terminal on, right when you get there you might notice a little arc, a little spark, but it can't really jump much of a gap. But if you were to try to do that with 2 wires on this electrical outlet, you could get them kind of close and it'll actually jump the gap, right? Do you understand why it would jump the gap if it's 120 volts? They're more motivated. They have a lot more electrical pressure. So does anybody have any idea how we measure electrical pressure? It's a term. There's the 12-volt battery or there's the 120-volt wall outlet. How are we measuring? What's the unit there? Volts, that's correct. Volts is literally our measurement for electrical pressure. So when you hear the term voltage, you're like, oh, okay, now everybody should get it. Now everybody's like, oh, if it's high voltage, that means it's got a lot of motivation to go, to be pulled through a conductor, to be maybe even jumped through the air, right? The air is not really a good conductor. It's more of an insulator. But if you have enough high voltage, it will arc through the air, maybe even into your body. You see what I'm saying? So I like 12 volts because 12 volts can't go through your body. It doesn't have enough pressure. Whereas when you get into these hybrid and electric vehicles, you know, they're 200 and something volts in the battery pack. Some of them are 400 volt architecture. There's some now that are 800 volt, right? A lot of, even like a Prius is a old 20-year-old Prius has 650 volts going to the MG2 to drive the wheels. You understand, the whole game just changed. When you're 12 volts and you mess something up, you're like, oh, whoops, I blew a fuse. When you're 400 volts out of the battery pack and you mess something up, it'll push through your body. Do you know what that means? You know what that means for you? Yeah, DED, dead. Yeah, so you could be killed. Okay, so now you really want to work on hybrids and EVs, don't you? That's also, you know, we have a lot of protocols and procedures. Okay, so now everybody understands what voltage is. It's just a measurement of the pressure having to do with how negatively charged or positively charged, which essentially means just how motivated those electrons are. Okay, and we got another term right here. The flow of electrons from atom to atom is called, whoa, what's that term? Current. Okay, so if voltage is pressure, current is more like volume. Current is how much, right? So voltage simply means what's the pressure of that electron trying to move. Current flow is like how many, how fast, like how many electrons are flowing. The more electrons are flowing, the higher the current flow. Okay, and later I do have a spec on how many electrons equal 1 amp, and it's like a lot. So if I were to say current flow, now you guys understand it's a volume. It's a volume thing, right? And how do we measure it? Well, it's measured in amperes or amps. We'll mostly just say amps. So if I say like 1 amp, you're like, oh, okay, that's like, that's like a lot of current flow. But if I say 100 amps, that's like that's like 100 times as much, right? So it all has to do with volume. Okay, makes sense. And then of course there's this term, it's not the voltage that kills you, it's the amperage. And I'm kind of like, yeah, I guess that's true. They say that, your heart could be stopped with only like 1 amp of current flow, but the thing is you need the voltage to be high to actually push through your body. So if you have a battery, for example, in a car has the potential for like 600 cold cranking amps. You're like, 600 amps? That would totally give you a heart attack. Yeah, but it's only at 12 volts. It can't push through your body. So my kind of rebuttal to it's not the voltage that kills you, it's the amps, is sort of like, while that's technically true, nothing happens without the voltage, so why are we acting like the voltage isn't a big deal? Like, if it's low voltage, it can't kill you. If it's got enough voltage to kill you, it does need the amps to actually do it. So has anyone ever been sparked by a spark plug wire or a coil? Oh yeah, you have. And you'll probably be sparked again. Why did you live though? Because those coils can be 40,000 to 60,000 volts, even some as much as 100,000 volts.
Low amperage.
Bingo. Exactly. So if you have enough voltage, it can actually push through your body, yes. But if it's like, 1/10 of an amp or less, you're just, it doesn't feel good, but you're not dead. So it's more like, ooh, like I don't want to do that again. Well, maybe one more time. Oh, okay, I'm good. After, like once, you know what you got. Twice, you're like, okay, yeah, I'm sure. If you do it a third time, there's just something wrong with you. I'm just letting you know. All right, so that's the concepts. And then we talk about free electrons. I'll give you a shot of that. Those are electrons located on the outer ring, which we'll call the valence ring. So that's the outer ring. Okay? And the thing is, the further out they get from the nucleus, it's honestly, the universe is pretty amazing if you think about it. It's kind of like planets, right? If the planets are going around the sun, the closer they are to the sun, the more tightly held they are, right? Then as you get further and further out, there's no real gravitational effect when they're further out, right? So you guys know if there's some, I don't know, asteroid or something, like that asteroid may not really be in Earth's orbit or in the orbit of the sun, right? So the closer you get to the nucleus, the more tightly bound they are, which would mean if they're in the outer ring, they're only loosely held by the nucleus. So why do you think that's such an important detail? Well, they're free to move from one atom to another when an electrical potential is applied, right? So when we have voltage that we apply, right, if it's on let's say a good conductor such as copper, you've got these electrons out in the valence ring. They're not really held that tightly because they're further away from the nucleus. So it just takes just a little bit of voltage and they're gone. Make sense? So if you had a conductor, you could still bounce those electrons out, but you'd need a whole lot of voltage. Does that make sense? Whereas if it's in the outer valence ring, like that's part of the reason that it's a good conductor. They're way out in the outer valence ring. It takes very little motivation for them to be gone. So if we were to look at like this one, if you look at copper, look, you've got this electron way in the outer ring. That sucker is ready to be bounced out, like with minimal voltage. Cool? And iron, similar. Iron maybe not quite as good. Look, we got 1, 2. Okay, but they're still pretty far out. Aluminum's pretty good. 3, right? So these are all good conductors because they have electrons way further out in the valence ring, way on the outside. Make sense? If we were to go back to, you know, like, let's say, argon doesn't show it real well here because a lot of times it has to do with how many protons are in there. But you'll notice, you're looking at 1, 2, 3 rings, and just looking at this, I'm going to bet you that's going to be very well balanced. And if you look back at that copper, you're going to look 1, 2, 3, 4 rings, and that's a lot of electrons. So that one's already really negatively charged, and this electron right here is barely hanging on for life. And that's kind of how it. That's kind of how you'd visualize it. And also the number of electrons in the valence ring are good. So if you consider that, right, we're saying right here, fewer electrons in the valence ring are going to be conductors. Look at copper, 1, right? Iron, it's got 2. So which is the better conductor? Copper, yeah. So why don't we only ever use copper? It's just cost. So sometimes we got to look at it like copper's better, but if you're trying to run wire, you know, let's say that someday you guys want to build a garage with a shop and all this cool stuff, and you're like, hey, that shop is going to be like hundreds of feet away from my house. You got to run wire out there. You want to price copper wire real quick, it turns into thousands, not just 1,000 or a couple thousand. You're like, hey, I need all this copper wire. And you're like, yeah, how many thousands? You see, and then you're like, aluminum. They're like, oh, $800. You're like, all right, fine, aluminum will do. Makes sense? So it's really a cost thing. However, this is what's interesting. If you decide to do aluminum rather than copper, you actually have to do a larger size aluminum. So we're right now just talking about really the different elements and how good they are as conductors or insulators, but the wire size makes a difference as well, especially when you start factoring how many amps are going to flow through it. You just visualize it like this. If you want to flow water through a pipe, a small pipe or a large pipe, which one's going to flow more water? The large pipe. If you try to flow a lot of water through the small pipe, it's going to start making, you know, a lot of pressure. It's going to be very difficult. It's going to be harder to get the water to flow through that smaller pipe, right? Like you're going to need to give it some more pressure to get the same amount of amps. Cool. So we get into that stuff a little bit too. All right. And then again, we talked about which one's a good conductor, which one's not a good conductor, the best and whatnot. And then we talk about what's an insulator. So plastics, for example. In insulators, what's it say? Electrons in the valence ring are bound much more tightly to the nucleus. So that all has to do with how many protons are in the nucleus and also how close the electrons are to the nucleus. Right? And then if you look, the greater number of valence ring electrons, the better the insulator. Let's see if that holds up. Look at this. 1, 2, this one has 3. Those are all really good conductors. Let's back up to argon. Look at that. 1, 2, 3, 4, 5, 6, 7, 8. Did I catch that right? 3, 6, 8. That's got 8 electrons in that valence ring. That's going to be a really good insulator. Those aren't trying to leave. You know what you'd have to do to make those electrons bounce out? You'd have to have extremely high voltage. You'd have to have a lot of pressure differential to bounce those out. Cool. So that's the trend. And then, like we already mentioned, semiconductors. That's sort of like, it's easy for it to conduct. It's more easy for it to conduct than an insulator, but it's harder to conduct than a good conductor. So it's kind of in between. And then I mentioned, for example, a transistor in a microchip. It can switch the material from a conductor to an insulator and back again very quickly, right? right? So that's kind of what's interesting. Remember I said computers speak ones and zeros. So a 1, for example, would be current flow. A 0 would be no current flow. How do we make current flow? We would actually send voltage to the control, and that will make it a conductor. If we take voltage away from the control, what will it make it? An insulator, and that'd be a 0, right? So it's really simple. 1 and 0 means on and off, which means conductor insulator, and we can do that. There's no moving parts, there's no switching, there's no nothing. So we're literally just switching them back and forth between conductor insulator quickly. And I'll show you a little bit of examples of that a little bit later when we get into components, but just keep that in mind. All right, pretty fun. All right, and then I think overall you should understand why electrons move, but here's kind of more how they move. So the free electrons, that's what we're talking about. If it's like 1 or 2 or just a few electrons in the valence ring, those are going to be free electrons. We'll bounce those out. When we want to move those, we need 2 things. A complete pathway, which we call a circuit. Make sense? So you guys have heard the term circuit. Now you know, if you complete the circuit, all you've done is given a pathway for the electrons to move. Make sense? That's what they need. And if you complete the circuit, they still won't move unless they have what? You see what's next? A force, right? So if we complete a circuit and we have a force, that will make them move. Cool? Okay, so in a car, how do you think we move electrons from the battery to the headlights? Yeah, how does it get to the switch though? The switch is true. The switch is either completed circuit or an incomplete circuit. In other words, a closed circuit, that's complete, or if we turn it off, it's an incomplete circuit, that's an open circuit, okay? But how does it get from the battery to the switch?
You made a path for the electrons to go through.
True. What is the path physically? Yeah, the wire, that's right, exactly. This right here, this is the path. The wire becomes the path. So if we've got a path, and we got the path, right, but what else do we need? All right, so how about, let me put it this way. What if your battery is totally dead? Are your lights going to work? Is the path broken? No. What's wrong with it? Why won't they work? It doesn't have the force, exactly. There's no voltage. So let's just say, we'll go old school. They used to have these things called the drive-ins, the drive-in movie theater. Some of you know, and some of you have no idea, and that's fine. You go to the drive-in. It'd be like going to the movie theater, except you don't go in the theater. You pull your car up and you park in a line, and you turn your radio to a certain station so you can hear it, and then you watch the movie from your car, right? If you want your radio to make the sound, so you can hear, what do you need to do with the car? You could leave it running for an hour and a half to 2 hours. That's crazy. No. What you do is you're just going to turn the key on to like accessory, right? You turn the key on to accessory. That's going to close the switch so now the current can leave the battery and go to the radio and make little pulses and make your ears hear the movie. And there you are watching the movie. And I mean, it's, if you're really into it, it's fine. But let's just say you're a little tired, the movie's not that exciting. What happens next? You start to doze off, right? Those electrons continue to leave the battery to play the sound so you can watch the movie. And next thing you know, a lot of times the drive-ins have 2 movies. So you may have fallen asleep in the first movie, slept through intercession, or they call it, whatever they call it, and then slept through the second movie. You think your battery is going to be charged 3 hours later? I don't think so. So then you wake up and you're like, oh, all the cars are leaving, let's go. You try to start the car, nothing. You try to turn the headlights on, nothing. Why? The battery's dead. But what's that really mean? That means you've essentially depleted the imbalance of electrons, right? So we have technically, okay, it's an excessive amount of negative charge on the negative side. That's why it's probably really electron theory that flies. But if you have a whole bunch of negative electrons packed all on the negative side, they're all leaving to play your radio, to play your radio, to play your radio, right? When you have a battery that's 12.6, that means you have 12.6 volts on the positive side and you have 0 on the negative. The differential is 12.6. If you leave your battery on and it discharges and discharges and discharges and you never start the car, it'll go all the way to 0.0 volts eventually. And at that point, you have no difference in pressure, right? So you turn the switch on for your headlights, you gave it the path. Why don't the headlights come on? Because there's no pressure difference in your battery anymore. So if you're to visualize your battery is simply a spot where you can store an excessive amount of negative charge and a positive or just a 0 charge, right? It's the pressure difference in the battery that makes the electrons want to move. Kind of make sense? So that's how we do it. Now, when you go to start the car, for your information, you turn the switch or you push the button or whatever, and we're going to close a relay. We'll talk about relays, but not right now. And the relay is going to send electrons to your starter motor, and your starter motor is going to do turn the engine over. That's what it's going to do. Then, assuming the engine's got the fuel and the spark and the compression, all of a sudden the engine's going to start running on its own, in which case you let the starter stop turning. Now the engine's turning on its own. Why is the battery charging? So the engine's turning the belt, and the belt is turning the alternator, and the alternator also uses electromagnetic induction to generate electricity pressure, electron flow, and put it back in the battery, right? So if you fell asleep in the drive-ins and you didn't start the car, like anybody who's a drive-in regular, you know, hey, when the first movie ends, you better start the car, leave it running for like 20 minutes because the alternator is going to recharge the battery. Now you're back to your 12.6 volts, right? Then you'll turn the car off, do ignition on or just accessory, and the radio will play, and it'll go from 12.6, 12.5, 12.4, and as long as you don't really get like much into the 11s, like you probably start the car at 11.9, 11.8, but if you start to get to like 11.0, I don't know that car is going to start anymore. You used up too many electrons playing the radio. There's not enough left to actually start the car. And if you can't turn the starter to start the car, you can't have the alternator charge the battery, so you're just kind of stuck. So at that point, what would you do? Yeah, jump it. So when you jump it, you're taking a charged battery that has a big pressure differential, like a 12.6 volt battery. You hook it up to yours, and that gives enough electrons to actually push through the starter and start the engine. Then you can yank the jumper cables off, and now your vehicle, once it's running, it's self-sufficient, right? The gas is burning, the spark is occurring, the engine's turning the belt, turning the alternator. The alternator's charging your battery. But what if you jumped it and then real quickly turned it back off? Your battery's probably not charged up enough. It takes time for the alternator to motivate those electrons to get back in the battery, get back in there. Make sense? So it's kind of a weird concept, but if you understand it, starting to understand it from like a physical aspect, I think it'll make a lot more sense. Okay, make sense? And the part that trips me out a little bit is when your battery's discharged, those electrons they're not gone. There's the same amount of electrons on the positive and the negative. So if there's the same amount on the positive and the negative, what's the pressure difference? 0. So that's when your battery's dead, totally dead. Kind of funny, huh? All right, so that makes sense. I think you guys should mostly kind of understand where we're going, right? The larger the charge between the negative and the positive, the more strongly the positive terminal affects the negative terminal, repels free electrons, right? So on a 12.6 battery, more voltage, more pressure. On a 11.2 battery, less pressure, and when you go to crank the car, you can tell. You ever notice when your battery is almost dead and you crank it cranks slow? That's because you no longer have a lot of electrical pressure built up in the battery. It's like, uh-oh, I hope it starts, because if it doesn't, I got to get a jump. What happens when we put the battery on a charger? Anybody know? The charger is actually going to make the electrons go and build the pressure differential up slowly but surely. The charger and the alternator, kind of the same. When you charge the battery, you're plugging into the wall, and that charger is generating the voltage difference to move those electrons and split them up and build up the positive, right? That part's always going to be kind of weird because just understand, technically, electrons are negatively charged, right? So it would be logical to think if the electrons are negatively charged, we're really packing the electrons on the negative side, technically. It's just weird. In automotive, we don't describe it that way. We'll say the positive gets charged. Okay, it's just a little weird. So the battery charger uses the wall power to motivate those electrons to charge the positive side up, charge the positive back up to 12.6. Your alternator does the same thing. It just doesn't take the wall power, it takes the engine rotation via the belt power. Okay, make sense? Same idea. Okay, pretty good, pretty fun. And then I think probably everybody will understand, in the vehicle, we're controlling circuits a number of different ways. So if you want to turn the headlights on, you turn them on with the little switch, right? You now made a pathway. So if you had the voltage and you made a pathway, the result of that is going to be a current flow. So the electrons will start to travel down the current path. They'll travel through the wire, through the switch, and to whatever. What do you want? The light bulb? Travel through the light bulb. And what do you get? Like this. Like this. Right. You get light in the form of heat. What if it's cold in the morning and you want to heat up your lower back? What type of technology could heat your lower back up in a nice car? A nice new car. Heated seats, right? How would you initiate the heated seat? Push the button, close the switch. Exactly. Then electrons will flow through this other wire, a different wire, through the switch you just closed, through your heated seat element, and at that point they'll give off energy right there, and they'll make heat, and it'll warm your back up. Right? Then they all go to the ground, which we will discuss. The ground is really just the negative terminal of the battery, but how they get there, they'll most likely go into like the body of the vehicle and then find their way back to the negative terminal. Kind of interesting. How about power windows? You like power windows? How do you make the power window move? Push the button, you push the switch. Again, you're going to notice there's a common theme here. The electrons are ready to go because the battery has voltage. You need to give them a path so that they can make it to the motor. And when they make it to the motor uses magnetism. The motor will go, and it'll put the window up or and put the window down. Locks, gauges, the radio, right? Tail lights, fuel injectors. We could come up with all sorts of things. The ejectocito, remember that? All the same. We get the voltage from the battery, we give it a path, but we got to control the path, right? So one of the things that we get stuck on is like, well, how do we control it? Most of the time we control it with a switch, right? You can control it with pushing a button. Or if we want, the computer can control it, but the computers don't have a hand to push a button. That's where we get into the semiconductors. And the semiconductor will make it so the computer can do ejectocito for us. And we could program it to say, hey, when we get up to 20, when you see 20 miles an hour, close this transistor, and that'll give a path for the electrons, and it'll bounce out the cuz, or whatever it is. So we've got all these different circuits. Make sense? It's really what we're doing here. Cool. So when we get more into the electrical aspects, now you got an overall view of the electrons, how they flow, why they flow. Right? When we get more into it, we got to know these terms. These terms are today's terms, right? Electrical resistance measured in ohms affects the current flow. So remember what we were talking about? Voltage is pressure, right? We all agree. Current flow is the volume of electrons. That's how many. That's like, if you have a tiny little creek, there's a small volume of water. If you have a big wide river, that's a much larger volume of water. Make sense? But The next thing is resistance, and resistance is just quite simply what's trying to slow the electrons down. That's it. It's just electrical resistance. If it was mechanical resistance, I would describe this as kind of like obstructions in the road, right? So if you jump on the freeway and there's nothing slowing you down, a lot of cars could move really fast, right? But if you jump on the freeway and there's debris and there's potholes and there's things and there's all this stuff, that's gonna put more resistance on your drive. It's gonna slow you down. So you're gonna have a lot less current flow if you have more resistance, okay? That's kind of the thing. So you now have heard all three of the major electrical terms for today: voltage, amperage, and now resistance, right? Now, how do we affect the resistance? Well, the type of material, the length of the conductor, the diameter of the conductor, and the temperature of the conductor. Let's break down one at a time. Copper has very low resistance, remember? Copper is a great conductor. If you were to have clean, nice copper, that's going to have very low resistance. What if you were to have pretty clean copper, but it was to actually have gotten battery acid in it, and then it were to make a bunch of corrosion, and now you have copper, but you also have this chalky white corrosion, and next thing you know, you get an intermittent no start on your car. You go to start it and it doesn't start. And then you go over there and you wiggle the terminal and now it starts. What's the explanation for the reason it won't start sometimes?
Loose connection.
Loose connection, corrosion, these issues, right? So if we have copper on copper, that's great. But if you have copper on corrosion, white chalky stuff, you no longer have a good conductor right there. That's going to have a lot of resistance, which means you're not going to have a lot of current flow, which means you're not going to have the car start, right? So the resistance was increased because we have not a good conductor. We have a corrosion in there. Make sense? By the way, when we say a loose connection, that's another good one. What if we had a truly not corroded at all, but literally loose? Is the copper touching the copper, or is the copper separated by a small gap of air? And if there's a small gap of air, is air a good conductor? No. So that's gonna add a lot of resistance. Make sense? All right, and then the length of the conductor. So believe it or not, we don't really want wires any longer than we need them. All right, so if you looked at the car and the wire goes from the battery to the headlight switch to the headlight, that's it. We don't have it go from the battery to the headlight switch to the trunk, around in 10 loops, have it be 100 yards long, and then go back to the headlights. That's going to actually add resistance. That's bad for current flow. That's not good. Now, if it's a little longer than it needs to be, just to give you some working length as you're doing a repair, okay. So if you had to do a wire repair and you needed this much wire, and instead you put in this much wire, it's not a big deal. But if you needed this much wire and you're like, I don't want to cut the wire, and you just put it like a bunch of loops right there, like that's not helpful. That's not good. So the length does change it. So remember I was saying maybe someday you guys want to build a cool garage and you want it to be separate from your house, and you're like, let me have it be out there. It could be the man cave, or it could be the she shed. Equally, it could be either one. If you want to run longer distance, that's going to add resistance to the circuit. Now you've understood it, because look, this is pulled right from the textbook, so you know. The length, the longer it is, the more resistance it's going to add. Do you know that there's a way we can account for that? So if you were to hire an electrician and be like, hey, I want to put my shop over there, and then be like, oh yeah, that's 300 feet, they're gonna run calculations. Electrical engineers, this is part of what they do. They'll be like, oh, you need a wire that's this big. Oh, but it's 300 feet away. Actually, you need a wire that's this big. Make sense? We can counteract the problem by the length by increasing the diameter. Make sense? So if it can be shorter, it can be smaller. But if it has to be longer, it has to be bigger. It has to be larger diameter. Make sense? And that all has to do with the resistance. I'm going to throw a new term in there just to start getting your minds thinking. If we increase the resistance is going to use up our pressure. Make sense? So if you add 12.6 volts, but you have a little bit of resistance, you're already dropping voltage. So the term is voltage drop. Resistance causes voltage drop. So if you had 12.6, but you ran the wires really far, by the time it gets there, it might only be 12.2. And you're like, why'd it go from 12.6 to 12.2? Well, that was the length, right? The longer the wire is, the more voltage it drops along the way. Kind of makes sense? As a result of the resistance. So if you were to do in a car, the thing's 20 feet long, maybe less, right? It's not a big deal. But if you're talking about like over longer distances, now all of a sudden you got to oversize the diameter to make up for the length. You know what also really, really helps with that? These two things are true. The length and the diameter are really important, but they're especially important at 12 volts. It's not as affected if it's high voltage. So you guys, nobody's living off the grid, I assume. You got some sort of power. That power doesn't come from your neighborhood. That power is coming from like a power generation plant somewhere. How are they moving it miles and miles and miles to your home? And the answer is, well, they have those substations and they'll bump the electrical voltage up. They won't do it in volts. They'll do it in kilovolts. So what the heck's the difference between a volt and a kilovolt? 1 volt.
1,000.
So 1,000 volts is the same as 1 kilovolt. So if you're like, oh yeah, it's X, Y, and Z kilovolts, that's because the power station is increasing the voltage because it helps it go better over longer distances. That's why those overhead power lines aren't this big. They don't need to be this big because they bump the voltage up to have it push through better, right? The more electrical pressure, the more it'll push through resistance. And then they'll step it back down to be usable for you. That's what a transformer does. So you ever see the transformer hanging on the side of the power line? Or like if you have a power pole, there's a transformer right there. It's because it's taking thousands of volts, dropping it down to 240, and then just dumping it into your house like, 100 feet away or something like that. That's what it does. That's why it does it. Okay, so automotive electrical, we're in our own little world here, but it's the same as other industries too. So if you do understand this, it actually can be helpful to understand other stuff. Okay, then another big thing is the temperature. So normally, the hotter a wire is, the more resistance it has. So if you have, let's say, a wire that is going to go to the starter to start the car. If you overwork it and overwork it and overwork it and you feel the cable and it's hot, that's adding resistance. You'll have a voltage drop through the cable itself. We want to keep it cool. How we keep it cool generally is we have it be short and large enough in diameter it should never really get hot. But like if, for example, you used a wire that was too small, it'll tend to get hot. And also, once it's hot, it'll add a lot of resistance. So the temperature is a big deal as well. Sometimes the specs on wire all have to do with the temperature too. Now, here's kind of the cool thing. All this has to do more with designing the automotive system. Does anybody have any interest in doing that? That's not what a technician does, so you know. Who do you think does that job? Exactly, correct. Yeah, so an electrical engineer needs to know this type of stuff better than the technicians because they're the ones designing it. As a technician, we could dumb this down. If you had a problem with the wire, you just need to replace the wire with the same size and type. That's it. That's all we do. The engineers figured out what wire size and what length and all that type of stuff based on how many loads are going to be on there, right? But the reason I feel like you need to know it better than just to be a technician is, remember, like I said, when you got that problem car, and it's being weird and it's doing weird stuff, like that Tahoe, I think it's going to be a ground problem because all those sensors that set codes share the same ground. Now, I was thinking about it, maybe the ground's a little corroded. That would add resistance. That would cause a circuit malfunction. But I also read some things. People feel like the grounds were undersized on those from the factory, so I could increase the size of the wire. Or I could add an additional redundant ground, right? So now I'm outside the box of just basically make it how it was from the factory. I'm more into like uncharted territory, so I justify these foundational understandings because you're going to get some weird stuff, right? Now, a resistor itself is a component that's designed to extract energy from the current flow by forcing it through a restriction in the circuit. What? I thought we didn't want that. Well, we don't want that when we don't want that, but we do want that when we do want that. So, for example, a light bulb. A light bulb is a resistor. We don't call it a resistor because it's a light bulb. We call it a light bulb. But in the circuit, it purposely adds resistance. And right here when it says a resistor is going to do what? Extract energy. Well, if a light bulb extracts energy, it basically transforms the electrical current flow into what? Heat, light, right? Isn't that what we want? That's the whole reason the headlight bulb exists. The headlight bulb exists to do one job. Take electrical energy and make it into heat and light so that we can see, to illuminate, right? What about the heated seat? What's the heated seat do? It warms my back because it's a little tight, overworked, right? That's its job. So it's not to say that the circuit should have no resistance. It's to say that the circuit should have no resistance where it shouldn't have resistance, so it can have all the resistance where we want it. A light bulb, a window motor, a starter, a heated seat pad, you name it. A radio that's going to make your speakers go bump, bump, bump. You know, you pick. What do you want? A fuel pump that's going to make the fuel go pump, pump, pump. I could write Dr. Seuss books if I wanted. Okay, so whatever the electrical thing is that's supposed to do work, that should be the resistor in the circuit. And probably most of the time from here out, we'll call that the load. The load does work. The load does some specific job, right? So I'm going to give you one more example of a load or resistor in the circuit that's supposed to be there, that does work. Some I haven't come up with yet. Anybody? Somebody? I got a fun one. The windshield washer pump. What's it do? Yeah, exactly. It should, right? So all these specific things do specific jobs. And the way they do it is we send them electricity and they take the electrons and they convert it into something more useful, right? Like we got electrons, what do you want to do with it? Make it turn a little motor that turns a little pump that scoops up windshield washer fluid and sprays it on the windshield. Make sense? Like it all does work. It all does a job. Now here's a visual of what we talked about. Here's a wire. And you can see, like in this image, it should mostly make sense. You guys can see we've got the voltage, and that's the driving force, right? That's the electrical pressure, if you will. And then, of course, we got the electrons, and the electrons are trying to move. And we got this hand trying to stop them. The hand is the electrical resistance. So it's the amount of opposition to current flow inherent in different materials. Okay, so like copper should have very little resistance, but corroded copper might have more resistance. That's going to resist the current flow, right? So if we had corroded copper, did the amount of amps go up or down?
Down.
Definitely down. Exactly. All right, so now, remember in the beginning I told you, customers come in with concerns for us. And I said, customer has a dim headlight bulb. A dim headlight bulb is most likely due to excessive resistance in the circuit. The reason I know is because remember, resistance causes the voltage to drop. So if we have corrosion on the wire or corrosion in the connector, we're dropping voltage at that point. Let's say it's at the connector. Cool? So let's say we had 12.6 volts going toward the headlight. It might drop a tiny bit across the switch, but it gets to the connector, and let's say it drops 6 volts. What's left for the headlight? Maybe 6 point something. A headlight's not going to glow that bright with 6 volts. You know that, right? You've seen your battery when it's almost dead. You turn your headlights on, they look kind of like gold or like almost brown. Like the more dead your battery is, the lower the voltage is, the less bright white your headlights look. They start to look more brown, golden, yellowish, right? If you're dropping 6 volts on a bad connection, that's going to be a problem, right? So that's what this resistance is. We want resistance, but we want the resistance where we want the resistance, which in that case would be the headlight bulb. If the resistance is somewhere else, the headlight bulb is not going to work as well. Dim bulb. If the resistance is really excessive, the headlight bulb may not work at all. And remember I was saying last week with strategy-based diagnosis, what do? Throw a headlight in there. Throw a new bulb in there. If it doesn't fix it, maybe try one more. Then if it doesn't fix it, tell them take it to somebody who knows what they're doing. I don't want that for you. I want you to be like, oh, the headlight doesn't work. Let me check, let me measure, let me diagnose. And if I check the voltage at the headlight and it's 6 volts, I'm like, oh, cool. If there's 6 volts coming in, that means I've lost 6 volts along the way. There must be resistance somewhere in the circuit. Makes sense? Now you're diagnosing. All right, and then the current flow, all that is, again, that's the amount of electrons that are actually flowing. Cool. So if we have higher voltage, that should make more electrons to flow. But generally in a vehicle, we're dealing with a pretty consistent voltage, like 12 point something volts. If the vehicle's running, technically it's going to be like in the 13 something, 13.6, 13.9, but right around there. So if the customer comes in with a problem, there's always the chance that the voltage isn't correct, but like it's a very small chance because, you know, it's a 12 volt battery, it's a 12 volt system. What are the chances that your battery is only at 4 volts? And if that's the case, the car's brought in for a different concern, right? Overall, the voltage is going to be a pretty easy thing to check. The most common problem on the vehicle today brought in is unwanted resistance, right? Unwanted resistance can be caused by corrosion, chewed wires. Anybody ever seen chewed wires? You ever chew wires in your spare time? You know who does? Mice. Squirrels I've even seen as well. I even had one. It's a neighbor. She's really nice. The dog's kind of unruly. It's like some Irish. It's the dog with no tail. Remember it's like some kind of a little shepherd thing. Okay, a squirrel ran over to the car and the dog got under there and started ripping stuff up. It ripped so many wires out it actually totaled the car. It was done. I mean, she asked me to look at it. I popped the hood and you could see like 80 wires just peeled up like that. I'm like, no, you're done. So, you know, that's more of a thing that we run into, right? Problems causing excessive resistance, that happens. What's the result? Well, if the voltage is generally pretty consistent, because if it's not, we just fix the battery or whatever. If we have excessive resistance, that's going to result in lower current flow. Things aren't going to work as well. If you don't have enough current flow, your starter doesn't turn the engine fast enough. It goes like this, right? Or if you have if you don't have enough current flow for a power window, you know what it's going to do? It's going to move really slow, or maybe not at all. What about if you have not enough current flow for the headlights? What are they going to look like? Yeah, you get me. Like, what if it was, you name it. Okay, how about if it was that windshield washer pump? If it had excessive resistance in the circuit, therefore not enough current flow and not enough voltage left for the pump itself, how's your windshield washer spray going to be? Maybe a little dribble, like, right? So like this is what we see every day. We see excessive resistance causing not enough current flow all the time. So just setting the stage for what you're going to really see. All right, so when we talk about the voltage. How do we determine the voltage? Well, we could just measure, right? 0 volts on the negative, 12.6 on the positive. That should be the amount of electrical pressure. And that doesn't really change that much because that's what the system is made to do, right? Now, that's not to say we couldn't have a battery issue, right? If you have a battery problem, which electrical components are going to be affected by the battery? Is it going to affect the headlights? Yes. Is it going to affect that windshield washer pump? Yes. Is it going to affect the starter? Yes, right? So if it's a battery problem, everything's messed up. It's not really hard to figure out when it's a bad battery. Make sense? Once we deal with the battery, if that is the problem, then it should be fairly easy to figure out where the problem lies with the particular component, right? So if it's all the components on the whole car, probably talking about like a battery, battery cable, battery terminal, you know, that type of thing. But if it's just one headlight, don't waste a whole lot of time checking your battery. It's not going to be anything to do with the battery if it's one headlight. If it's 2 headlights, you know they both go through the same switch, so I might put some effort there. But if the tail lights are good and the windshield washer motor is good, if all that stuff is good but it's only the headlights, I don't think it's going to be a battery. See what I'm saying? All right, and then when we talk more about the circuit, here's why you need to know that. Right, we'll go a little more and then we'll take a little break. So we've got this positive voltage buildup right there, as you can see. This is trying to push out. It's trying to push through this thing. What's this thing right here? This gray thing.
The wire.
Yeah, that'd be the wire, so we could call that the circuit or the wire. What is this thing right here? That'd be the bulb, and in this case, it's the resistor of the circuit. You may also call that the load of the circuit, right? So sometimes we're going to use different terminology, but in this case, the planned resistor is the load, and it's in the form of a bulb. Okay, I could rip this bulb out, and I could put a little motor right there, and it could be the windshield washer motor, and it would be the exact same diagnosis. Okay, and then so the positive wire goes to the bulb. Then it leaves the bulb and it goes to this thing. What do you think this little thing is right there?
Switch.
Yeah, that's true. What do we do with the switch? Yeah, open or close. That's how we control it. If there was no switch and we just hardwired it, what would happen with that bulb all the time?
Be on all the time.
Be on all the time. Your battery would be dead. You'd be like, why don't the lights turn off? Right. So generally, we have some sort of control part to the circuit, right? So right here I made a note. If I close this, that gives me a complete circuit. If I get a complete circuit, what should start to happen with the electrons? What do you guys think? Come on,
They're
dude.
going to move.
Yeah, they're going to move. That's exactly right. You close this circuit, now there's a path. If this circuit's open, there's no path, right? So the second you close it, they start flowing, and that's why the light comes on. That's why the lights light up. That's exactly right. Now let's talk about, just apply the terms. There's a complete path. That's the circuit, right? That's the loop. The loop always has to go from the positive all the way back to the negative. It has to. The electrons can't go from the positive into the car next to them. They don't, that's not how this works. We need to have a pressure differential between the positive and the negative. They always loop all the way back. Okay, does that make sense? Now, and sometimes we'll call this a source of higher voltage. We may call it power, but right now I'd like to define some terms. I really like voltage better because voltage is more specific. Voltage is telling you the electrical pressure. However, it's very common. A lot of people will say, oh, the bulb doesn't work. Check for power. And I get a little choked up at that point, and I'm going to explain to you exactly why, and then we're going to move on. I'm not going to let it ruin my life. Okay. Voltage is pressure. So if you put your meter on volts, and you probe right there, and you get 12.6, you did not check for power. You check for voltage. That's why the meter's on volts. Power is a equation. It's volts times amps. P equals V times A. If you have it on volts and you probe it and you get 12.6 volts, did you check amps? So why are we saying we check power? It's not really true. We just check voltage. If you want to check amps, by all means, you got to put your meter on a different setting. You got to break this circuit open and you got to measure it in a totally different way. And then if you checked volts and then did a second measurement to amps, then you could say, yeah, I checked power. But like, you didn't check power. That's just not accurate unless you did two measurements. Okay, so you check volts. However, I try to stay in line with what the industry's doing. In my time, we called it checking voltage. Currently, there's so many people. You know how they say ain't a word? Yeah, but it's in the dictionary, though. So now it is, right? So when I came through school, like, don't say ain't. Ain't is not a word. And now it is. When I would say we check for voltage, I was good with that. And then other people would be like, we check for power. And I'd be like, I'm just going to let it go. And then 15 years later, they're like, yeah, we check for power. And I'm like, well, actually, you're wrong. But then on the ASE, this industry standard exam, they say check for power now. And I'm like, what? How did we get to this? I knew it was wrong all those years ago, and I just let it go. And now the ASE is saying no power at the bulb. Okay, so now you guys understand power in its truest form is volts times amps. And if all you checked was volts, you didn't check for power, but I'm going to let it go. We're letting it go. We're going to say power is voltage. From now on, if I say there's no power at the bulb, just understand I really mean voltage, but I'm just trying to roll with the punches. Everybody else calls it power now. And I could prove my point, but nobody cares. Except for you, maybe. All right. So with that, there's a power, that's positive voltage, and a lower voltage, which is ground. You know what we mean by ground? See the negative? That's ground. All the ground is just the negative terminal of the battery. Some other industries would call it a common. Other ones will call it earth. We're just going to roll with ground, okay? So if I wanted to check this bulb, I need to check for a positive voltage here. I need to check for a negative voltage here. It's hard for me, all right? I'm going to check for power and ground. Ooh, that was tough. That's just wrong. All right, I'm going to check for 12 volts here. That's checking for power. I'm going to check for 0 volts here. That's checking for ground. Okay? Everybody knows. And then if I wanted to measure the actual current flow, I would check in amperes. Which I generally, there's probably no reason for me to do on this one. Now let's just say effects of current flow, right? So we yank this bulb out and we put in something else. How about a starter motor? That's going to make what? What's the starter going to give me? It's not going to give me light, right? What's it going to give me? Motion, movement, motor, rotation. It's going to give me some sort of movement. Make sense? What about a defogger? What's this going to give me? Heat. Yeah, that's going to defog the windshield. Or if you're, up in the mountains, that's going to actually melt the ice off. Exactly. And then the battery's kind of tricky. Chemical energy is kind of weird, right? So if we just look at what we can do with current flow, we can make light, which technically is just heat, but it's heat in a visual way. We can make movement, and that's going to be kind of complicated, and we're not going to cover that today. That's going to be like electromagnetic induction, and we can make things move based on the current flow. It's pretty cool. Or we could make heat, not for visual, but to actually melt ice or clear fog off of a glass. Now, chemical energy, this one may trip you out a little bit. If you think of a battery, I kind of fibbed to you a little bit that, oh yeah, there's a whole bunch of electrons over here and they all want to make their way over here. Like, not exactly. What it more is, when we charge this battery up, we're adding electrons here, and what it's really doing is it's changing the chemical composition inside the battery. And when we change the battery more from watery to more like battery acid, it has more of a voltage potential. And we'll get more into batteries, but we have stacks of plates in here, and those stacks of plates in the battery acid make a voltage. And the more we charge it, the more acidic it becomes. Technically, it's actually more alkaline, but the more it changes away from water, and we basically store our electrons, but not in electron form. We store the energy of the electrons in a chemical form. You're like, what? What just happened? And then at any given moment, if we need electrons, we'll just change this acid into a little bit more watery, and it'll spit out electrons. Pretty much magic, basically. But we also spend like a whole class on the battery, so I think I've said quite enough. Okay, makes sense? So it does store electrical energy, but in the form of chemical. Okay, kind of weird. All right, then we got just a little more, and then we'll take a little break. So talk about this a bit. Let's talk about conductors, good wire. That's going to be good for current flow. It's going to be very low resistance. Okay, so low resistance means this hand is not blocking the electrons. That is measured in ohms. Okay, anybody ever heard of ohms? Maybe somebody? It has a lot of ohms. Yeah, exactly. Okay, a good conductor has very little ohms. And ohms we abbreviate with this omega symbol, which is Greek. Okay? And then if it has a lot of ohms, that means it has a lot of resistance. The ohm number will be higher. Right? So a good conductor will have low ohms. 0.2 ohms is really low. 0.0 ohms would be as low as you can go. But if you had an insulator, for example, air is an insulator. If you took a meter and you just held it up and the positive and negative were separated like this, you'd probably get like mega ohms, which literally means millions of ohms. Right? Then if you brought them together and touched them, you'd probably get like 0.2 ohms or something. Very little ohms because the electrons can conduct through the wire that's on your meter lead. And then if you hold them like this, they're not touching, that's going to be a lot of ohms. So if I wanted to test a wire, I could actually measure the wire in ohms. And the wire should be maybe like a 0.2 ohms. But if the wire is like 1,000 ohms or 1,000,000 ohms, that wire is not a good conductor. Why not? I don't know. That's what we got to find. Maybe the mouse chewed it. Maybe you chewed it. Maybe it's corroded. Maybe there's a bad terminal fit and there's an air gap in between there, right? Like, so we can measure that. See, so remember when I said in strategy-based diagnosis, you don't just throw parts at it. If you think it's the switch or the wire or whatever, just measure it. And then if you measure it, you're proving that it's good or you're proving that it's bad, right? That's your mind state needs to be, I think it's and then you measure it and you confirm, or you're like, nope, the wire checks out. It's not the wire. Move on to something else. Make sense? That's what we're going to do. And then semiconductors, that'd be more like computerized. They'll use, there's one that silicon, like silicon chips, semiconductor stuff. All right, so let's relate the resistance factors. And then I think it'd be a good time for a break. Okay, here we go. If we have longer wire, more resistance. Shorter wire, less resistance. Okay? If we have small wire, more resistance. If we have larger diameter wire, less resistance. Okay, make sense? So these are true all the time. If we have the wire and it's hot, more resistance. And if it's cold, less resistance. Okay, make sense? Generally, though, and I'm speaking mostly from a technician standpoint, if you're working on buildings or you're working on a custom car or something that somebody did in their backyard or their basement, you might run into stuff like this. Okay, but from a technician, because that's me, and that's what this class is. So somebody else figured all this out. The electrical engineer figured out the wire size and the length and all that type of stuff. If you have a problem with the circuit, you know what it's more likely to be? This. So let's discuss. If you had broken strands on the wire, what do you think the effect would be?
Dim light.
Yeah, dim light. So isn't that going to give us more resistance? Would you guys agree? Because look, right here, we gave you the truths. If you had a big wire, less resistance, but if you had a small wire, more resistance. Well, this might have been a big wire, but now you only have a couple strands left in there. Isn't that more resistance? So you may have a dim light. You may have a slow cranking starter. You may have a windshield washer motor that only goes and it won't even get up on the windshield, right? Like all these are going to be the result of these nicked wires, broken strands. Now, how would these get broken like that, though? In a car, how do you see that happening? Some of you seen some stuff, so tell me, what have you seen? I already gave you the rodent example. Don't give me that again.
If it hangs a little bit under the car and it's like...
Yeah, maybe it got hit, maybe it got drugged, maybe, you know what I've seen too? People don't run the wire right and it drags and it touches the exhaust and the exhaust burns it. Next thing you know, there's just a little bit of strands, right? So physical damage happens quite a bit. There's also a thing called chafing. As you get older, you'll understand more. If a wire's rubbing, it'll rub through. It just chafes. If you get, let's say it's a wire for the alternator and it gets routed wrong, the belt could actually rub through it. We've also seen on some cars, you know, your engine shakes a lot and it just moves. So if you had a wire that's sitting on the engine vibrates, it'll rub through a spot. It'll cause damage like that. What about somebody worked on the car and that harness is supposed to be clipped into certain spots and they do the job and they're like, you know what, I broke a couple clips, just let it go, ship it. Well, if it's not where it's supposed to be and now it's moving around, don't you see how over time that could cause damage to some of the wires, right? This is the stuff that we see as technicians. We see this a lot. How about, so like these ones are broken strands. This one's nicked, but I want to go into this a little further. This one didn't damage the actual copper. If it damaged the insulation on the wire, you know, that's like rubber or some sort of plastic. On some of them, it's some soy-based material, which is partially why the rodents like to eat the wires. But let's say that we damage the insulation. Why is that going to be such an issue? Especially in the elements, rain, salt at the beach, salt on the roads, and the snow. Why is that going to be a big deal?
Has a problem in the circuit.
True, but have you ever seen metal that gets exposed to water and salt, corrosion? Bingo, exactly. So you may have a wire where the strands aren't broken, but just the insulation having a little cut in it will cause moisture, salt, and etc. to get in there and actually corrode the wires. And your copper wires are good conductors, but not when they're all corroded and nasty. So I just had a kid call me the other day. He wants to put up a backup camera in his vehicle, and I've done some work for him, and I'm like, you know what, I don't really have time to do the radio thing for you, but you could do it. Like, just do it like this. And he said, yeah, when I connect the wire to my reverse light, I used like a wire nut. You know what a wire nut is? There's wire nuts up in these, in a building, a wire nut's fine. If there's water coming through this roof and getting into the wire nut that's behind this switch panel, that's a bigger problem, right? Like, the wire nuts are good enough in a home because they're watertight inside. But on a car, he's trying to make a connection outside the car, behind the tail light where the reverse light is. Wire nuts said, no, heck no. Absolutely not. How is a wire nut going to protect from corrosion? It's not. They're not sealed, right? They're open. It's just an open... He might as well just twist the wires together and just maybe put like a little bit of tape on it or something. So it's like, no, that's not going to hold up. In fact, it already didn't hold up. It wasn't that it corroded, though. It just didn't hold them tight enough and it ripped apart. It's like, yeah, when I put the taillight in, the reverse camera stopped working. I'm like, what'd you use? A wire nut. No. Go back in there. If you want to do this, you need to use something that's watertight. So when we do wire repairs, when we do testing, you're negligent if you start piercing that insulation and not fixing it. I'd say don't pierce the insulation at all. Some people would say pierce it and then fix it. I would say don't pierce it at all unless you really had to, in which case if you had to put a nick right here, you need to do like a good wire repair. What I told this, I'm going to say kid, to do was, look, if you need to add a wire right here and join them, cut the wire in half, strip this end, double your wire up. So he's going to have two wires on this side, one on this side, and then you're going to run it in a heat shrink butt connector. So you're going to butt connect it with good crimpers, crimp it so it won't pull apart. But then you're going to heat it up with like a lighter, a blow dryer, or like a heat gun, and it's actually going to melt, and it's going to totally water seal it. You want to know how good the water seal is on those? I repair wires, and I put them underwater in my pond for lights for years, and I have no problems. So if you actually do a good job resealing the insulation, you'll have no issue. But if you don't, you might not have an issue today, but the corrosion will get in there and make more and more and more resistance, and then you'll end up with the dim bulb or the whatever. A lot of times, if I get a car that has, you know, this type of thing, you want to know what the number one reason for pierced insulation is? I've seen pierced insulation caused by probing tools, by razor blades, pinching thing. It's two-legged varmints. You ever heard of those? That's other technicians. Yeah. So people working on the wires are usually the ones who will pierce the insulation and just just kind of ignore it. And then someday later, it becomes really hard to find. So I had one with a daytime running lights and op at one point, and the customer brought it in. I was like, I don't know. The daytime running lights are, I don't remember if they were dim or in op. I think they were totally inoperative, so not working. And I systematically check the wiring diagram. I measure voltage, and I've got voltage at the fuse box, but I don't have voltage at the actual daytime running lamp. So I'm losing it between the fuse box and the running lamp. The problem is it leaves the fuse box and it goes behind the front bumper. It's out of sight. So like if I know I have it here and I know I don't have it there, I know it's in between, right? So either A, I sell a whole new harness, or B, I pinpoint where the defect is and maybe I can repair the wire. We do that. But what do I need to do to test it further? It goes behind the front bumper. I got to take the whole bumper off, right? So this customer authorized 1 hour to diagnose the lights, and I called back after an hour and I said, hey, it's between here and here. And they're like, all right, what do I need to do? And I said, well, it's for me to really know exactly where the defect is and exactly what repair you need. I need more time. And they're like, what? More time? I've already paid a diagnostic. And I was like, yeah, that really means you authorized an hour of my troubleshooting, and I got to the point where I know it's between these 2 points. I can't test any further until I remove the bumper. By the time I remove the bumper and do further testing, you know, and then I have to be able to put the bumper back on, you're really going to have to authorize at least another hour or two. And the customer had a fit, called their friend and said, my friend said you should be able to find any electrical defect within an hour. And I kind of said, I can tell you it's between A and B, but how do you think that's going to cover the time to pull the bumper and do all this type of stuff? Like, I had to really defend myself against this customer. So you guys got to understand this as well. If it's something that you can tell where it is, but you can't tell exactly what, you may need to spend more time to really figure it out. So I sold them pulling the bumper. I did more testing. Take a guess what I found. Prior technician, here's a guess, had done a repair, and when they went to put a new wire in, when they try to open up the harness, they just grabbed a razor blade and they just went right along the electrical tape and cut all the electrical tape off. So when I got in there, I found, hey, there's resistance here, and I located the wire and I grabbed it. It's kind of corroded and like a little green. Sometimes we'll call it like green disease. I'm like, oh, I know what wire it is for the, I think for the DRLs it was purple. So I'm like, oh, there's a purple wire. I bet you that's it, right? It's only a few feet away from where I could test it, but it's in a black conduit all wrapped up. I can't see it that well. So I'm like, oh, there's a purple one. And I look, it's all green disease, chalky. So I make a measurement, and it was like, I think it was like 6 volts right there. And I'm like, 6 volts? I'm surprised that wouldn't at least make the lights come on. I test a little bit further. It's at like 3 volts. I test a little further. It's at 1 volt. It had been pierced like 3 or 4 times all the way across this whole, behind this bumper, where the last tech was just ripped it with a razor blade. If you pierce the insulation, not a problem right then and there. This was years later. This was one of the harder lighting problems I've had, because it was like It wasn't the bulb. It was dropping voltage. It was behind the bumper. So, that was kind of dirty for somebody to pierce the insulation in several spots. If you pierce the insulation, you know it, fix it. If you just wrap it up and act like it's fine, somebody may spend several hours finding that spot that you just kind of buried. So that wasn't really right. All right, and then the last thing on these would be corrosion on like maybe a terminal. So we got a ground right here. The wire's crimped to the eyelet, and then we bolt it down to the frame. Maybe we've got corrosion underneath it. Maybe we got, sometimes I've seen where, you go to bolt this down after freshly painting it from the body shop, and you don't clean the paint off. You think paint's a good insulator? No. So if you just go ahead and you throw your ground right over top of the paint, there's a good chance that that's the cause of the excessive resistance and therefore voltage drop, right? So these are the types of things that we see. And so the fix for this one would really be unbolting this, cleaning up all this rust, maybe even putting a little bit of a dielectric grease or something, bolting it back down. The cool thing is with each of these, it's not just a visual. You can actually measure it, right? So we can measure the resistance, or we could measure the voltage drop between here and here, and then fix it. And then how would we verify that it's fixed? If we can measure the defect and then fix it, can we measure it again and see if now it's a good measurement? So that's closing the loop, right? That's more like a verification that we actually fixed it. Whereas DIY people will be like, oh, I see corrosion. Let's just clean all the corrosion, put it back together, and then guess whether or not it's fixed, right? So get on to where you measure and you can prove that it's bad, not just say like, oh, I see this, I see that, I see this, I see that. You don't see electrons. You can see signs, I agree. You can see the corrosion, you can see green disease, but like, you don't know for sure that that's the issue unless you can measure it and prove it's the issue. And then verify it. All right, right now this is my recommendation. Let's take a couple minutes because we got a little bit more to cover, but I'm going to say, let me pause this. All right, here we go. Next focus is going to be, oh, you better knock it off. All right, the components. So if you look, here's your basic circuit. It has to have resistance, as you can see, which in this case would be the bulb. The bulb is measured in 10 ohms. It has to have wiring, which you can see in gray, and all the wiring, the fuse and everything has about less than 0.1 ohms, okay? So if you really look at this circuit, we've got the source. The source is the battery. That's where the voltage, electrical pressure comes from. The electrons are going to leave the positive, go through the fuse. Does anybody have any idea what the purpose of the fuse is?
If it's current going through,
Bingo.
protection.
See, you know something. So I'm catching on to you. I'm catching on. So the fuse is to protect the circuit. You could think of it as like a sacrificial piece. Like a sacrificial little lamb. If there's something wrong over here where, let's say, maybe we get shorted out and there's going to be too many electrons, the fuse will blow. So it's circuit protection. We could get rid of the fuse, and we could also use a circuit breaker if you wanted to. And sometimes we'll even use fusible links. And we'll talk about more of those in the next several lessons. But right, so we got the fuse that protects it. We got the wire. We got the bulb. We got all this wire down here is what we're going to call the ground side, okay? Before the load is the positive side, because that's going to have 12 volts, right? 12.6 or whatever. After the load, it should be 0 volts. That's the ground side. Now, if you look at the resistance, we've got 10 ohms on the bulb, and all the other stuff combined should be like less than 0.1. So if this was dollars, it'd be like $10 for the bulb, and all the resistance and all these other things should only be like 10 cents. Right? So do you see how the bulb is pretty much all the resistance on the whole circuit? That's on purpose. We want the resistance to be where we want it to be, which in this case is the bulb. Right? And then if we look at, there's this new law we're about to introduce. I told you today is going to be very scientific. We're going to talk about Ohm's law just as an exposure, and then 2 weeks from now, you're going to do Ohm's law calculations. Okay, you're going to be a scientist. All right, but for now, according to Ohm's law, a circuit that has 1 ohm of resistance and 1 volt, like a 1 volt battery, will have 1 amp of current flow, right? So that's the baseline. There's this relationship between how many volts, how many ohms, and how many amps, and they're always predictable. And you can, if you know 2, you can figure out the third one every time. Make sense? So electricity is never like this mystery, like, oh, well, in this case, the electricity acted different. It's like, no, it doesn't work that way. It's Ohm's law. It's a law. That's why I was saying, like, the way that things work is, it's very interesting. It's mathematically proportional. You can do math and determine the outcome every time. It's a very clean design how it's set up, right? So if you had 1 volt and you had 1 ohm, you would have exactly 1 amp. But in this case, we have 12 volts and we have 1 ohm, and so therefore we would have 12 amps, right? I'm not teaching the math right now. I'm just letting you know, electricity doesn't just switch it up. Electricity does exactly what it does every time. It's very predictable, and that's why it's not Ohm's suggestion, Ohm's guidance, it's Ohm's law. It's the law of science. Okay, pretty cool? So from there, if we have higher voltage, that will produce more current, right? Why does that make sense? If you had more pressure, don't you think it would produce more flow? Heck yeah, it would, for sure. What if we had lower voltage? If you don't have as much pressure, don't you think it's going to have less flow? So that's true. Now, this is true from a theoretical standpoint. I mean, it's true in real life too. It's just, in the vehicle, like what I was saying before, this battery voltage is fairly consistent. So we're not usually looking at this part of it. We're not looking at, oh, the voltage is high or the voltage is low. What we're more looking at is probably, like back here, the resistance is most likely what's going to be the variable because of wires getting chewed and damage and things like that. So we could actually interpret this in a different way, right? If we look right here, if the resistance went up, the current flow goes down. That's a little bit more applicable to what we do. If the resistance goes up, the current flow goes down. So let's get an example. Why would the resistance go up? Corrosion, loose connection, damaged wire. Maybe, that's probably the most realistic. I mean, maybe the wire got really hot. That would make the resistance go up, right? But in all these cases, let's pick corrosion. If the corrosion is, if it's a loose ground on the frame and it's corroded and there's high resistance, what's the effect going to be? The resistance is up. What's the effect of current? Current goes down, right? So that's more where we have to think, right? If you have, maybe you have a connector that goes to the headlight and the connector is burnt and overheated and now it's a loose fitting, you have increased resistance. That means your current flow is going to go down, right? If resistance goes up, current flow goes down. Now you're kind of understanding why the bulb is dim, right? If the resistance goes up, the current goes down. But what if it's the other way? What if the resistance went down? What would the current do? Wow, it's predictable. Exactly, it's exactly linear. It's literally, you can calculate it. Now, if I were to back that up, remember, this bulb has 1 ohm. All right, check this out. What if this bulb was replaced with like a 0.1 ohm? It had 1/10 of its design. And we were expecting to have 12 amps due to 1 ohm. If we had 0.1 ohm, we would have 120 amps. It would be 10 times more amps because 1/10 of the resistance. Why is that a concern? That wire is not going to handle 120 amps. That wire will be on fire if it got 120 amps. So,
The fuse would work.
bingo, that's the purpose of the fuse right there. So if you don't know what you're doing electrically, please just put a fuse in there. And if the fuse blows, it's because it's protecting it. So don't put a bigger and a bigger and a bigger fuse in there and blow those up too until the fuse like imagine if you put a 120 amp fuse in there, the fuse wouldn't blow, the wire would actually be the weak point at that. If you actually put too big of a fuse in, now the wire would get hot and catch fire and burn the car to the ground with the occupants inside, potentially. Just saying. It could go that extreme. All right, so that's the purpose of the fuse. And we can predict some things. So again, the electrical engineer more does this. Here's the math. We're not going to do the math today, but in 2 weeks you will be doing this math and you're going to love it. If you wanted to figure it out, you could literally look at volts is E, that's electromotive force. I is current flow in amps. R is resistance in ohms. You draw this little circle. If you knew the volts and the amps, if you knew E and I, you could literally just do the, let's say, yeah. If you knew E and I, you could literally put your finger over the R, and do you see how E is kind of like over I? That's E divided by I. Okay, makes sense? So if you had 12 volts of E, and you had a current flow of 12 amps, what's 12 over 12? 12 divided by 12 equals 1. Isn't that what we said right back here? 12 volts divided by 12 amps equals 1, and that's correct, 1 ohm. Right? So just saying, this is not, it's not a mystery, actually. It's just a little abstract. You can't see it. You can't count the electrons. You can measure them, and you can calculate them. Right? Now, let's just say you mixed it up. You didn't know the voltage, but you knew how many amps and how many ohms. You could cover the E, and you could do amps times ohms, I times R. See how they're next to each other? You make that like a little X. It's I times R. Right? And so if it was I of 12 times R of 1, what's 12 times 1? 12. Wait a minute. We had 12 volts. So you just see, we're just proving it. We're just proving it over and over. What if we had, what if we knew the voltage, we knew E, and we knew the resistance was 1? Wasn't it 1 in this? Yeah, it was 1. So what if it was 12 volts divided by 1 ohm? That would equal 12 amps, right? So you can calculate it in every different way, and it'll always turn out to be correct. That's Ohm's law. Now, you don't get to do the math today, but trust me, you're just going to love it. You can do math on math on math. Today, we're just going for the overall. It's the introductory. Ohm's law is how we understand electrical flow, which is very consistent, it's predictable, it's measurable. You can get the right number every time. You can't be like, oh, well, this electrical problem was different than all the other ones. It just doesn't work that way. Now, can they be hard to diagnose? Absolutely, especially when they're intermittent, especially when there's other factors involved, such as it's happening when the customer's driving it, not when you're driving it. You don't exactly know what is going on in that moment. They can be difficult to fix, but it's not because the electrons act different on that day. They're always the same. Who wants to get this as a tattoo? Nobody? Lower back tattoo, perhaps? But good. You also notice it's there, too. I didn't put that picture up. Somebody else did. This is a fun picture just to help you know the relationship. Mr. Volt is trying to push Mr. Amp through the resistance, right? Through the rope of resistance, let's just say, right? So this is a cartoon version of how electricity works. So what do you think would happen if Ohm yanked up on that rope a little tighter? Amp wouldn't go through as well, right? There'd be less amps. If you increase the strength of ohms, you're going to decrease the amps going through, right? What if volt pushed even harder? That would push more amps. What if volt pushed a little less? That would push less amps. What if ohms released the tension and now it became really easy? Amps would go up, right? So there's just this cartoon version of what we just proved with Ohm's law. Make sense? And the main thing we look at in automotive is probably we don't have enough amps, and it's probably due to excessive resistance. There's always the chance it could be to insufficient voltage, like the battery source voltage is low, but we look at those problems just a little bit different. In a typical circuit, we're mostly concerned about what the resistance is in that circuit. It's just what we're running into. Now you could look at it a couple different ways. Like if we had a water tank, do you know the pressure on this water tank all has to do with the height and the volume? So if you had a big volume right here at this 6 foot height, that would make a certain amount of what we call head pressure, right? So there are places, I mean, typically not here. Like when you turn on the faucet here, you get water pressure because a water station is running a pump and pressurizing the water main for a whole neighborhood, right? But in some areas, they'll just go up a mountain and they'll actually get a spring, and then they'll run a pipe down a certain number of feet, and that will generate pressure. The gravity will generate a pressure. So not so much here, but in other places they do, right? So right here, we have a certain amount of pressure. It comes down the hose. Why is it only dribbling right here? Could you catch it? There's a kink. The kink is excessive resistance. So you can all visualize. All right, you've had brothers and sisters, right? Let's say, we'll make it nicer. Little brother. Little brother, you're like, hey, go check the end of the hose, and you kink it, huh? You're like, yeah, look in there. Do you see anything? Like this. And then what happens? You unkink it, right? So you kinking it is adding resistance. You're decreasing the flow to maybe just a dribble. Makes sense? That's what happened right here. Now, in a hose, it's very visual, and that's why we like to tie it to a hose or water flow in a pipe and stuff. But with electrons, it's kind of similar. You just can't see it, so it's harder to understand. So if we have excessive resistance, you're going to get very low current flow, right? Now, technically, it'd be true, like if this water got down to just the very bottom, especially if it was at lower height, you'd have very low voltage, and that could be the result of low current flow. But in this case, we're confident that the voltage is good. We just think it's due to excessive resistance. There's probably a kink in the hose. You would find that if you're just dragging the hose around the car, trying to wash it, and it all of a sudden dies out. You probably got it kinked under a tire or something, right? Electrical is kind of the same. If we were to look at it like this, the battery is the source of pressure like the tank. The wiring is kind of equivalent to the hose. Then, of course, with electrical, you know, we're controlling it with a switch. That would be like the valve, like the nozzle. You know, either the nozzle or it could be the valve where you actually turn the spigot on. Could be either one. That's how we control it. And then after that, we're going to have it do some work. So in this way, I mean, we're not really having the hose do work, but let's just say we're to hook this hose up to like a little like a, almost picture, how about, not a windmill, but what would you call it? A water mill. What do they call? You guys help me out. It's we wouldn't have it be like a water turbine. What the heck would we call it? What do they call it? At a dam. What do they call this? How do dams make electricity? Google knows. Let's say, yeah, we can see that. Oh, like a hydro dam. So let's just say that we had the water coming out of here and we had it spinning some sort of a device, right? If you had a kink in the hose, it would no longer spin the device. Make sense? So in a way, you got to understand this water should be doing work. That would be spinning the device in a hydroelectric dam or something. With electricity, what's the work that's supposed to be performed right here? What is the work that's supposed to be performed? Well, it's a rear window defroster. So we're trying to use electricity to make heat to defrost or defog the glass, right? So it's the same type of thing. If you had a kink in the hose, it wouldn't turn our dam. If you had excessive resistance in the wire, in the switch, in the fuse, whatever, it wouldn't make heat for you to defog your window. Make sense? So it's that simple. Customer comes in and they say, oh, my rear window doesn't defog, and you'd be like, okay, cool. Let me troubleshoot the electrical system and figure it out, right? And you can do that reliably. It's just not as simple as look for the kink in the hose, because the wire, you can't really see the electrons. Cool? And then when we talk about the resistance, just keep in mind, the electrical energy is in the electrons, and when it goes through a resistor, it's going to lose electrical energy, right? But then we got to go back to, well, remember what I said, like energy can't be created or destroyed. It's really just transferred, if you think about it. So if the electron had energy and we sent it through a resistor and it lost energy, where did the energy go?
In the heat or something?
Bingo. Exactly right. It became heat. Correct. So if we have unwanted resistance, that's what's kind of interesting, it can become heat. And so I've seen some people do some really interesting troubleshooting where they'll actually use like thermal imaging cameras, and they can find resistance through heat, location of heat. It's pretty cool. So if you think about that, right? So if we had a resistor, that's going to be heat. Now, if it's a good conductor, it should have low resistance. So what should the temperature be if it has low resistance? It should stay pretty cool. Yeah, exactly. Now, if you had too much resistance in a wire, it's going to make heat. But what's kind of weird is if you have excessive resistance in a wire, it's going to lower the amount of amps, right? So it may not necessarily get hot because now you have less electrons flowing through. You just end up with a much lower current. It's kind of interesting. Okay, and then if we look at resistors, and we'll cover components a little bit more, but just so you know, when we're working on circuits, electrical engineers figure out, you know, what voltage and what resistance, and they do all their things. And if they want to add a resistor, they can do calculations like this. Each one of these bands means something. So when I went through school, we spent a bunch of time where honestly back in those days you could throw me a resistor and I could look at the bands, and they wanted us to be able to tell what the resistance was of that resistor and plus or minus how much, what's the tolerance, right? So like, for example, the last band, if you had a silver, that's a 10% tolerance. But if you spent some big bucks and you got like this red, you'd have a 2% tolerance. And it was really interesting to know, and it was kind of fun, and it was totally useless fixing cars. I didn't need that. I didn't benefit from that. But I did think about whether or not I should cut it from this, and I decided to leave it because I want you to know if you get into an electronic part and you see a bunch of these, those are resistors and those bands mean something. And if you're to the point where you need to know those colors, you're outside of really what I do. And it's not to say it's not valuable, but it's not valuable to the everyday technician trying to fix the car. This isn't really what we do. We just don't do this. Cool? But so that's how they work. There used to be a store called Radio Shack. Some of you don't know, but you could go to Radio Shack and you could buy resistors. So that's what they had us do for class. We bought some certain resistors, and we would basically hot glue some stuff together with a certain resistor and then a red LED and a different resistor and a green LED, and then we'd actually put it in a tube, and we made ourselves a little, they call it like a logic probe or a smart test light, and you could actually tell what was 12 volts and what was ground. It would light the red LED or the green LED. It was a pretty neat little thing to make. You can buy them cheaper than you can buy the material, and Radio Shack has been gone a little while, so I'm sorry to let you know. It was a fun thing back in the day. All right, so if we look at it from here, let's say the current flow is going to increase. If the current flow through resistance increases, the voltage used by that resistance will increase. And you're like, what? All right, let's figure that out. The current flow through resistance goes up, the voltage used by that will increase. Okay, this is a new concept now. So what I'm saying is, if you send voltage through a resistor, it's going to consume the voltage. So let's say we start with 12 volts. If you send 12 volts through a resistor, and assuming that you're going to have actually like a substantial current flow, it will decrease in voltage. So the reason we want to know that, you start with 12.6 at the battery, you send it through some wires, then you send it through the bulb. The bulb is expecting to get 12.6. It's going to consume 12.6. And when it consumes that 12.6, it's going to give you a consistent amount of light, nice bright light. And there's going to be a specified current flow depending on the voltage and the resistance. Make sense? That's how it's designed. When we add resistance, that resistance is going to consume voltage. Make sense? Because it's going to continue to flow. So that's what this is saying. If the current flow increases, so even if the current flow stays the same, if we increase the resistance, it's going to consume that voltage. All right, so if you send the 12 volts out of the battery and it goes through a damaged wire and the damaged wire consumes 6 volts, how much does that leave for the bulb?
6 point something.
Yeah, exactly. Depends. So let's say it was just a flat 12 volts. If the resistance consumes 6, that only leaves the bulb with 6. Make sense? So a lot of times the way that we as technicians will diagnose it, we'll measure the voltage. If the voltage dropping across the bulb is 6, that tells me something else has consumed 6, okay? We're going to spend like a couple hours on that concept because people get really stuck. But I'm just showing, in the fundamentals of electricity, we're showing some of the laws, and that's why that's predictable. So if we measure a voltage drop, we can determine how much resistance it is. It's kind of interesting. Cool? So when we diagnose the circuit, a lot of times we'll use a voltmeter to look for excessive voltage drops that reduce the available voltage at the load device. All right, so now I'm explaining, you could measure resistance. I agree, you can, and resistance is good. But when you go to measure resistance, you have to turn the power off and you have to use your meter to measure resistance. That's kind of like saying like, hey, I want to test your heart. So we're going to basically like isolate your heart and test your heart specifically. It's not really as accurate of a test as if I were to say, you know what we're going to do? We're going to check your blood pressure and your heart rate, and we're going to have you jump up on a treadmill and exercise. You can get a lot more information dynamically, make sense? So if you were to remove an electrical circuit and test the resistance, that's fine. But it shows you a little bit more if you leave the electrical circuit plugged into the power source and you measure the voltage at different points, it could tell you more info, okay? But just so you all know, technically, you could diagnose the circuit with resistance. It's just normally we use voltage. I'm trying to make you understand. Using the voltage tells us the resistance. Make sense? If we measure the voltage drop, that's going to tell us that excessive resistance caused it. Cool? Kind of weird. And the relationship between current, voltage, and resistance, it's all predictable. It's all calculated using Ohm's law, and that's why we do what we do. Okay, so that's kind of the direction we're going. When we go to do these measurements, though, we're going to get into the meter. And the meter, how to use the meter, how to measure, how to hook it up, that's a whole different day. But just so you know the direction we're going, if you wanted to diagnose the circuit and you wanted to measure voltage, you got to know how to use the meter, and you got to understand when you measure the voltage, how to interpret that information, right? So most of the time, the service manual doesn't say measure from here to here, and if your voltage is 11.2, do this, or if your voltage is 12.6, do that. Like a lot of times you just look at the diagram, and you should be able to understand the diagram and know what the voltage should be, and you should be able to predict it and then measure it. And if it measures and it's good, then you know it's good. But if you measure it and it's bad, you have to be able to on your own be like, oh, okay, that could be this. That could be excessive resistance in the switch. That could be a short to ground. You see what I'm saying? So you got to actually know a lot of how this stuff works to be able to fix the car, but to be able to pass the test as well. So we'll spend quite a bit of time on this, just so you know. Remember I told you I was going to give you this spec. I just couldn't remember it. If you measure 1 amp it's equal to 6.28 billion electrons traveling past a given point in 1 second. Okay, so there you go. Will I remember that? No. I didn't remember it last time, and I'm not going to remember it this time, because I'm never going to be like, oh yeah, there was like 6.28 billion electrons flowing through that wire. Like I counted them. 1, 2, 3. Like, come on. What I'm just going to say, an amp. I'll be like, yeah, there's 1 amp. And the only reason I know there's an amp is because I'll measure it, right? And so we mostly speak in amps, but now you know 1 amp, 6.28 billion. But notice it's going past a given point in 1 second. So when we talk about amps, it's as if like you generally what we do, we open the wire up and we send it through our meter and we make it go in the meter and back out the meter so that the meter can see every single electron that goes through that 1 point. Does that make sense? So the way we measure it's a little bit different. Now you know if I say an amp, you're like, oh yeah, of course, it's 6.28 billion. Duh. Okay, I'm just not going to remember. Okay, so if that's true, we can do it like this, which is inductive, which is approximate, or we can actually open the circuit up and measure it real, which is not that easy to do because you actually have to disconnect stuff. Okay, just so you know. So now you know what an amp is all the way. And then an ohm is, remember, that's the resistance. That's the one pulling up on the rope. It's used to describe the amount of electrical resistance in a circuit or component. So, all right, so let's say we're going to talk about this part, which is an injector. If you wanted to measure the resistance of the injector, look, you had to disconnect it. Then you have to hook your meter up to it. And then this meter is going to use its own little battery. Typically, it's a 9-volt battery. And it's going to substitute its own little 9-volt battery and send electrons from its 9-volt battery to go through the component. And it's essentially going to measure how hard was that? Was that really difficult? If it was really difficult, your ohms are going to be high. If it was kind of easy, your ohms are going to be low. Because remember, the ohm is like the amount of electrical resistance. Okay? But you got to notice, to check this injector, again, we had to disconnect it. Right? So you're checking it, and it's a good way to check it. But a lot of times we'll actually measure the voltage to determine the resistance, because we're measuring it dynamically when we're actually testing it operating. Go ahead.
When you're measuring something like the resistance using ohms, does it matter, like the polarity?
Sometimes yes and sometimes no.
So
On a solenoid, no. So this just happens to be something I know. I would not expect you to know this like coming right out of school. Normally when you're doing a test, you're following some documentation. You wouldn't just be like, oh, just let me like randomly measure this thing. So typically you're following service info and you're testing what they're calling for you to test. I know, for example, a regular light bulb, bidirectional, doesn't matter. You can test it either way. An LED, an LED is single direction only. If you test it in reverse, it won't give you a number. In fact, most of the time testing resistance on an LED won't even give you a legitimate measurement because the voltage it uses isn't high enough. You need a meter that's going to do a diode test function. A solenoid, same direction either way, but it depends. So, and sometimes yes, yeah, it is possible you can get a bad reading, fall asleep.
Did we really open up this circuit somewhere in the car to measure the current?
On our boards, when we do our testing in class, yes. On the car, typically, no, but in some occasions we will. But normally what we would do, the best place to measure current is if we pull a fuse. If you pull a fuse out, it's already open. Now you can run your ammeter from fuse terminal to fuse terminal. So maybe, but it's not like a daily thing. What I would never do is be like, hey, I need to measure the amps here. Let me cut your wire and measure it and then like put the wire back together. Like that's kind of like if you went to get your nails done and they busted out like a chainsaw. And they're like, yeah, well, we can do it with the chainsaw. I'd be like, whoa, chill. Like, can we do something a little less invasive? I don't want to get hacked up. So if we work on the car, no one should know. Make sense? Like, if you work on the car and then it was like, oh yeah, they did that because you see tape all over the place, like that's not very good quality, you know. So it'd be kind of rare, but we do sometimes. There's certain examples, like sometimes we'll get a weird fuel pump issue, and it'll be like you really want to know what it's actually drawing, and you might, but it shouldn't make a mess. It should just be right at the fuse. This is pretty common though. The inductive, because you guys, what you can't quite see on this inductive just goes around the wire. You don't have to cut anything. You just put it around it, and they're pretty good. They're just not that exact. So when we're measuring a starter and it's 125 amps, this is great, because who cares if it's reading 126 but it's off by an amp, you know, that's pretty good. Maybe it was really 125. But when we're trying to measure like an electronic component and it's off by an amp, that's a lot, you know. So different tools for different jobs. Right now, if you guys mostly understand measuring ohms, just understand the meter does it with its own internal battery, and it's a good way to do it. And if your number is higher, that means it's more resistance, and if your number is lower, that means it's less resistance. And if you want to measure a wire, you could measure the wire, but you have to disconnect the wire, and then you have to go to one end of the wire, and then you have to go to the other end of the wire. You got to stretch your meter way out. So like measuring ohms is fine, but pretty quickly when we get into this, you'll realize why we're typically measuring volts, even though our concern is ohms. Because remember, volts can tell us ohms because of Ohm's law. That's kind of the point. All right, and then when we talk about circuits, let's go over the basics. Power supply, fuse, switch, and a component that performs work. We're going to call this the load. And then wires. All right, so let's take a look. Power source, fuse, switch that controls, and then the load. And of course the wires. That's your basic circuit right there. And you should be able to, in the next month, be able to predict what voltage should be where here, and you know, be pretty educated. And then remember, the power source creates the voltage difference. So that's the potential. So if you ever hear a thing like, oh, what's the potential? You're kind of like, why are we using so many terms? Voltage is potential. It's a difference in potential. I would probably just go with voltage myself. But if you do hear that, just so you know. All right, then when we talk about the current flow, again, the current flow is the actual movement. So if I were to say voltage, that's pressure at varying points. So if I had 12.6 volts right here, that tells me nothing about current flow at all. That just tells me how much voltage, how much pressure there is, okay? When we say current, that's the actual movement, right? So if you want to know how much movement there is, you actually have to measure amps. You have to measure different. Voltage doesn't exactly tell you amps. You could figure it out. If you had voltage and resistance, you could figure out amps. Make sense? But a lot of times if you actually want to measure amps, if you want to know what the amperage is, we're actually going to measure that. If you want to know what the resistance is, it's kind of interesting. Sometimes we'll just use voltage to determine, even though we might not get the exact number. We have different ways to figure out different things. And then I think overall you guys understand. When the filament on a bulb heats up, the resistance goes up, but that's okay because we're getting the light that we want. So one thing that I've seen is if you measure amperage of a bulb, you think you got a number, and then you write the number down, and then you look back and it's different. You're like, what the heck? And then you look back and it's different. Why is the amperage decreasing with time? Take a guess. Let's make it 1 amp. Boom, you start measuring amperage, and the amperage is 1 amp. Then it's 0.9, and it's 0.8. It's 0.7. Why is the amperage going down with time? Well, what's happening to the filament? The filament heats up.
The heat's not as hot.
All right. Let's think about if the filament heats up, its resistance increases. Hold on. If the resistance increases because of temperature, what happens when the resistance increases? Right? So just so you know, some of these things, when we start doing these experiments, you'll be like, whoa, that's weird. But weird is good because you can figure out why it's actually doing it, right? So if the current's going down, that's because the filament's still heating up. Once the filament's as hot as it's going to get, what's going to happen to the current flow? It's going to stabilize right there. Then if you were to turn it off for a bit, let it cool down, and turn it back on, the current would be kind of high again. It's not because the electrons are like being stored up or changing direction. It's just the resistance is changing with heat. That's it. You know, so what seems complex, if you get down to the bottom of it, you're like, oh, okay, it's not that complex. It's pretty simple. Cool. And then semiconductors is a point that I'm not in love with, mainly because if the electrical problem is in the harness and in the component, we fix that. But if you diagnose the electrical problem, the failure, as inside the computer, generally technicians, we don't fix that. Now I've seen a few exceptions where somebody will actually open up a computer and magnifying glass and put a ground strap on and actually try to desolder and resolder. That's not the norm. So like once in a while I'll see somebody that's really impressive. That's more of an electronics person who happens to be working on the car. If you bring your car to a shop with a technician, if we know it's inside the computer, that's it, we're done. Guess what we're going to fix? We're going to replace the computer. We're not going to solder things. Is that your question?
My question was sort of like, because I had a thing I made like this a while ago.
Sure.
That I had to recap the ECU on it because all the caps were bad.
I see.
Something like that, if you were taking it to a shop, would they just went and wanted to replace the whole ECU then?
Oh, for sure. Yeah. For a number of reasons. I mean, it starts with, can we do a repair and have it be reliable, right? So like if you have enough work to do that every day, you can get good at it.
For me, it's the difference between $30 and $300.
Oh, for sure.
So,
and if you can figure it out, cool. But figuring it out's one thing. I'll get involved in all sorts of squirrely stuff that normally I wouldn't if it's mine. For example, I've even done fiber optic splicing. Like nobody does fiber optic splice, but it's an 1,800-foot fiber optic cable that I cut through. So I'm gonna fix it, you know. But would I do it for a customer? If somebody called me right now and they're like, "Hey, I was digging in my yard and I cut the fiber optic line. Will you fix it?" I'll be like, "No, I don't do that." And they'll be like, "Wait, I know you did yours." And I'll be like, "Yeah, but it's different if I do mine to save the money. If I try to do it for a customer, it needs to be reliable because if it fails, they're coming back to me. It's going to ruin my reputation." So if there's a shop that has enough business to do electronic soldering repairs inside of computers, then probably they could get good at it. But that's pretty rare, and everyone's a little bit different, and we don't get enough real like repetition on that. So 99% of the time, if you have a problem that's inside the ECU, PCM, BCM, whatever the module is, let's get a new one. We're done. What I'm going to focus mostly on, it's interesting though, what I'm going to focus on mostly is, can you diagnose it 100% that it's in there? That's what I don't want us to be like, well, technicians, we don't repair computers, so let's replace it to start. Like, that's not what I'm saying. What I'm saying is, if you diagnose the external as good and you know the internal is the problem, that's good. But you have to actually get to that point and diagnose like that. That'd be the goal. Okay.
We'll know that by the end of the class. How to
Yeah.
diagnose the inside.
Yeah. Mainly the way that we diagnose the inside is essentially we diagnose the outside. And if the outside is good, that only leaves the inside. And there's a few things we can do to verify it's the inside. Like I'll actually show you in a second when we look at transistors. We can measure up to the point of the outside, and that'll tell us kind of what's going on inside. But we really, mostly what we really do is make sure the outside's good before we suspect the inside, and then we can nail down that it is the inside without going inside. That's our goal. And we do that quite a bit. All right. So when we talk about electronics, that's mostly inside, okay? So I'm going to tell you some things about transistors and stuff, and you have to know how they work, but truthfully, I've never replaced a transistor. I don't think that I can replace a transistor. I can verify it's a transistor and then sell the part that contains the transistor, okay? So to give some context. So some of this is love-hate for me because this isn't really like my hands-on experience beyond diagnosis. But if you look at electronics, we're talking about devices in which electrons are conducted through vacuum gas or semiconductor. And used to be vacuum and gas, but now we're going to talk about semiconductor. Semiconductor is computer chips, right? So you all understand. If it's in the computer chip, I don't replace individual parts. I replace the whole entire computer. You might become a little more specialized. That'd be cool. All right. The semiconductor's electrical resistance is higher than most conductors, but lower than most insulators. Remember, they're kind of in between. So they can be a couple different types. The negative electron or the hole, and this is not really a big deal here. Just so you know, there's different types. The number of charge carriers can be altered by adding a very small quantity of impurities to a semiconductor material, and they'll call that doping, and they do different things with the material, how they make the material to make it to, more desirable effects. So like one of the examples I give you is the type N or the type P semiconductor. So in a moment, we're going to look at NPN and PNP and just understand it all has to do with how they make the material. Excess electrons are N, holes, which is not enough electrons, are a P. Okay? So for example, here's an N and here's a P, and you can see there's a lot of electrons, and here you can see not so much. Missing electron, for example, makes it a P. Okay, and in detail, truthfully, I told you the truth. I don't know, I don't really even know how to determine this. You do a microscope or what? I don't know. I just know how to diagnose it, and I am very comfortable with that. So let's go with this one, for example. This is an NPN. So they use this N material and this P material and this N material. So see, it's kind of like a sandwich, sandwichy. So if we do an N, a P, and an N, we can send current into the collector. And let's just say the battery goes to the collector, and we want to control a light bulb over here. Would you agree we need electrons to flow into the C collector, go all the way through the P, and go out the N and go light the light bulb? You'd agree with that, right? The way that we would make current flow from C all the way to E, from the collector all the way to the emitter, is we'd have to give a little positive charge on the P material, but a very, very small current flow. Computers are really good at this because they'll take your main battery voltage in C, and then we'll have a little computer chip control B. And if B gives a positive, the current will flow through this semiconductor and go out E and light the light bulb. So what did I describe? It's basically like a switch, right? If the switch is open, there's no current flow. But remember, the computer, if it's a switch like this, the computer can't open and close that. You understand? There's no mechanical way a computer can move something. So what we do, we give these transistors. And so if we have it like this, the computer can give voltage to B or not give voltage to B. If the computer gives voltage to B, what happens?
Current flows?
Yes, it flows. That's like the switch is on. But what if the computer doesn't give voltage to B?
No current.
It's like the switch is off. See, so when I look at transistors, a lot of times we're mostly just looking at a switch basically. But there's no physical switch. There's a NPN or a PNP transistor, and it just controls it like a switch. So let's just say this switch was a computer. If I wanted to diagnose it, I'd be like, all right, is there 12 volts going into the computer? Yes. Is the computer supposed to be closing the switch, which is really a transistor? And if it's supposed to be closing it, shouldn't we get like 12.6 volts coming out? But if I don't have 12.6 coming out, and I do have 12.6 going in, I'm sorry, but that transistor is not working. And therefore, I'm going to sell the computer. I'm not going to sell the transistor. The whole computer is getting replaced, right? But what I need to do is make sure that the computer is actually trying to close the switch. In other words, I need to make sure that the computer is giving voltage on the B, on the base. And that can be a little harder to do, but a lot of times what I'll do is I'll go in with a scan tool and I'll purposely command it on. I'll say, headlights turn on, and that way the computer is speaking, the scan tool is speaking to the computer, computer to computer, and saying make sure that that transistor has positive going to the base, so the current should definitely flow. And if it still doesn't flow, it's no good. But what if I were to have a blown fuse back here? If I had a blown fuse back here and I didn't verify it's getting 12 volts in, isn't it possible that it could have a good switch or a good transistor and it could have just been the outside fuse, right? So we need to make sure the externals are good before we condemn an internal computer stuff. And that's really where we're trying to go with the electrons, right? So at this stage, you're just trying to basically understand. In the computer, there's not a bunch of levers and things and little gremlins run around throwing levers and stuff. It's solid state, which means nothing moves. We can do PNP or NPN, and it'll conduct or not conduct depending on if it gets something at the base, right? That's what's going on in there. So we talked a little bit about the PNP and the NPN. If this one right here is an N, a P, and an N, and it needs to get positive on the B. If this was a PNP, that would have to get a negative on the B. But other than that, as far as I know, who cares? Like, I don't understand why the exact difference would be that important to us. What I need to know is it getting the voltage in and is it getting the voltage out correctly? That's the extent of what I know as a technician. If you want to do the repairs, this is what it looks like, right? This is more of an electrical electronics technician, and they have a ground strap right here because these circuits are so tiny. Your little static electricity, it'll blow a big old crater in these tiny electronics. You can't have any static discharge if you're going to work on these, and so that's why this is not done like at the shop in the grease on the top of the toolbox, like with you scuffing your feet across the ground. Zap, we don't do that. This is like a little more controlled, clean environment. It's just a different job, and if anybody wants to do this job, that's great. It's just not what I know. It doesn't mean that you could not be amazing at it and make maybe as much money or more. I don't know. It seems to me a lot of this type of work though is mostly been outsourced. Like some of the stories I used to hear back in the day, there was a lot of places that did computer refurbishing, and now it's sort of like they're online based, they're not local, and sometimes they're not even in the United States. They're outsourced because they'll send a bunch of them over and they'll pay somebody a lot less money to do this type of work. I think they would do the same with the whole car if it was easier to ship the car, to be honest with you. It seems to me that working on the actual physical car and doing service is less likely to be outsourced because you can't quickly ship it across the ocean or something. But if any of you get into this, you can let me know. There's a little more details, like saying the conductivity can be manipulated or controlled depending on what they do, with the material and whatnot, and the PNP and the NPN. And we'll get into Hall effect a little bit, but probably not a lot in electrical 1. That's electrical 2. And also, we can do stuff with photodiodes and LEDs where if it gets a light signal, it will change its conductivity. So like, if you really want to trip out, if we went back here, we could use a type of a transistor that will conduct only when it sees light. And so when we talked about fiber optic, that's more what fiber optic is. Fiber optic is going to be pulses of light. You can use an LED to pulse a light, and you could use a photodiode on the other end to interpret the pulses of light. And now you want to talk about computer communication. Remember, on and off, that's all computers know, ones and zeros. What if it's LED on, photodiodes like, okay, that's on. Now you can transmit information from way over there to way over there just as quickly as the computer can, right? So we could send pulses, electrical pulses, or we can send it with light too. That's all electronics. That's fiber optic. So if you hear the term Fios is like a fiber optic tube, and we're pulsing light on one end and we're interpreting the light on the other end. That's sometimes that's your internet right there. And then the materials we're using a lot, like silicon, be very common. Again, and that's just because we can make it a conductor or an insulator. It's kind of in between. And we'll use different types of things. So like different types of silicon carbide, for example, we'll do blue light emitting diodes, and they can be better for heat. And Germanium was one of the first ones. There's all sorts of different chemicals, and this is something that's being researched all the time. But it's really specific to electronics, so I'll give you a little bit of it, and then mostly we'll go away from this because it's not exactly basic, and it's also kind of not what we do. So if you're going to fix a car and you think knowing how many electrons are in arsenic, I have never been asked that, and I don't know how many electrons are in arsenic right now, and I'm fine with that. All right, so it's just showing you. These are semiconductors, semiconductors, and they combine them, and they do different weird things. Okay, so electronics, do you love it? All right, do you love AC and DC? Not AC-DC, just AC and DC. How about DC and AC? That way we're not confused as what I'm talking about. All right, right here, DC. Right here, AC. Who knew that? DC's direct current, the electrons go one way. AC is what? Alternating current, which means it alternates. So the electron, it doesn't go from positive to negative. It goes more from like positive to negative, back to positive, back to negative, positive, negative, right? So if we were to graph that in voltage, you'd see the voltage was as high as 3 volts, and it flips and it goes down to negative 3 volts. So if it was positive 3 volts, it's pushing the electron. But if it's negative 3 volts, it's pulling the electron back. Which one do you think is more common in cars? DC batteries or DC? Yeah, so the car's main source of power is the battery, so therefore the whole car is DC. There's a few parts in the car that could be AC. What about in a building? AC or DC? It's AC, actually, and the reason why, at the other end, you know, you get the power from the wall, but at the other end of those wires is a power generation plant. It's probably coal-powered, just saying. I mean, it's most likely solar. Yeah, during the day. 10 at night, they fire up the big old diesel, coal, some kind of generator. Right, well, that thing spins. The generator spins. Spinning things make AC, right? Solar actually does make DC, but because the whole grid is made for AC, we have solar that makes DC, and then we invert it to AC, or convert it, technically, to AC, and then it makes AC. So it's weird. So if you have a solar system, you need an inverter that's going to make it from the DC to the AC. But basically, your whole power grid is AC power, but your car is DC. Okay. There are some reasons why you'd want to switch back and forth between both. If you want to check an outlet, put it on AC. If you want to check a light bulb on a car, it's going to be DC. Once in a while, things on cars are AC. A speed sensor, for example, could be AC. But for now, you're just understanding. DC is electrons go one way and it's usually consistent. AC, electrons go back and forth and it's switching back and forth. And how many times it switches per second is the frequency, right? So I'd say AC is a little more complex. So we'll just probably keep it simple, stupid today. DC is mostly what we're into. However, if you're trying to measure AC and you have your meter on DC, it won't measure anything. You'll be like, oh, I got nothing. And then I'll look and I'll be like, hey, your meter's on AC. That's why you're getting 0 volts on the battery. Flip it to DC, bang, 12.6. Your diagnosis was thrown off because you didn't have your meter set right. Your meter has to know, am I looking for AC or am I looking for DC? If you have it set wrong, your whole diagnosis is going to be wrong. Okay. The other way too. If you're trying to check AC, if you have it on DC, you're not going to get anything. Okay, so that's kind of what we talked about. The frequency is measured in hertz. That's how many times it flips back and forth. This thing called a sine wave, that's what this is. It's a sine wave. It's rounded, it's up and down. DC tends to be square. AC tends to be oscillating. And this is really because this is made generally by something spinning. The magnetic field is not on and off. A magnetic field is weaker, stronger, 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 weaker, 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 weakest, stronger, stronger, strongest, weaker, weak, right? So this is natural for a spinning thing. Typically in a computer, computers don't ramp on and off. Computers go on and off. So if it's computerized, it's going to be a digital signal. That's not going to look like mountains and valleys. That's going to look like a city skyline, squares. Okay, just so you know when we get into it. All right, overall, fairly good. So you know, though, you guys have heard the term alternator. The alternator makes AC voltage, AC current, which is no good for our battery. So we invert it into DC, and that's all built into the alternator, so you know. But the alternator actually does make AC. We just convert it to DC before it leaves. So as far as you know, it makes DC. Just does it through its regulator rectifier. Okay, and then let's say it's hybrid, though. And this is where it gets complicated. AC motors tend to be a little more, they tend to work a little better. They're a little more powerful. They could be more reliable. So if it's a hybrid vehicle, you may have a DC system that converts to AC, and the AC powers the big motors, like the traction motors, like this, ones that do burnouts and go 0 to 60 in 2.4. Make sense? So it's not uncommon if you have a hybrid or EV that the actual drive motor is AC powered. The way you'd know, they typically have 3 wires rather than 2. 2 is typically DC, 3 wires is typically AC. And I could go into it, but we'll just keep it simple like that. How about that? Cool. So that's kind of the good news and the bad news. 99% of what we do is DC, unless it's a hybrid or EV, in which case the motors are probably AC. Cool. And in a car, when we want to make DC into AC, we need this whole inverter setup, and they're going to use insulated gate bipolar transistors, and these can make an AC waveform, an AC current from DC, but it's kind of expensive. Like, inverters are expensive. That's what they are. Okay, so like here's what that actually looks like. Right, this could be either way. If you had this as an alternator, this spinning thing is going to make an AC waveform, and we're going to send it into this inverter, and these are going to switch so fast it's going to come out as DC. Cool, that's an inverter. We invert that. Or it could be the other way. Let's say you have DC going to the battery, or DC coming from the battery going to the inverter. The inverter can make your DC into AC and turn your motor. All right, so who's ever heard of regenerative braking? You ever heard of that? I just explained it to you. Right? Okay, that's if you are all hybrid and EV. Hybrids have regen braking too if it's a true hybrid with an actual drive motor. If you're accelerating, DC leaves the battery, goes to the inverter. The inverter is going to invert it to AC and make you go vroom, vroom, vroom. Okay. Acceleration. But then if you start to go down a hill and it does regen braking, it doesn't squeeze the brake pads. You going downhill will drive the motor. The motor will actually send voltage back to the inverter, and the inverter will take the AC, convert it to DC, and charge the battery. Okay? So just so you know, there's all this AC and DC going on when it's hybrid EV.
Is that the 3-wire system that you were talking
Yeah,
about?
exactly. So once I see the 3-wire, that's my clue that this is AC. So you see you have multiple poles here, and it's going to be red, blue, red, and orange. And those 3 phases of AC go into here, into this inverter, and that inverter will be switching these IGBTs to make a nice, clean, beautiful DC. The inverters are amazing. It's literally, this works just the same as a solar inverter. So if you have solar, at home or the neighbor or somebody, that solar is making DC and this inverter is making clean, beautiful AC and powering everybody's stuff. It's the same with a car. We switch them back and forth. Cool. And then the other thing that's a big deal that you got to understand to give you a good perspective, that's the purpose of today, introducing and give you some perspective, is on the cars, we usually use a positive coming off the cable doing some work, and then the negative really just goes to the chassis ground. So essentially, if you were to look at your car, you got your positive terminal, and it goes out to the fuse box and to the lights and to the switches and to all these places. Then you look at the negative and you're like, what's up with that? It just comes off the battery and goes a foot over and bolts to the frame. And you're like, huh. Well, the reason why, it's just a savings. Why run a positive and a negative wire to everything, right? If you had to run a positive and a negative wire all the way back to your taillights, it's kind of silly. So a lot of times what we'll do, we'll run a positive wire to the taillights, then it'll go through the bulb, and then the negative will just come off the bulb and then go to like the trunk or to the bumper. And then the bumper, because that negative goes to like, let's say the bumper right here, or let's say it's way at the back, those electrons will actually get into your frame, into your chassis. We'll say, you know, chassis, you don't pronounce the S at the end. It's not chassis. It's just chassis. Although you can say whatever you want. If you say it enough, they'll make it true. It's already happened a few times. Power. Right? So if you just send the positive back there, and then you have the ground, and the ground just goes to the frame or the chassis, then the electrons are actually going through the frame. Then they'll get up to this point, and they'll jump on this wire, and then they'll go back to the battery. So the whole negative of the battery is grounded on the chassis. So you guys know, any shiny, exposed, clean metal, that's going to be ground on a car. And that's why.
Ground structure?
Yes, exactly. So and sometimes we'll run multiple and redundant. That's what I'm thinking about doing on that Tahoe, is running another set of grounds just to make up for the first ones. But this is not going to be positive. This is going to be negative. Okay, makes sense? So like, if for some reason this whole ground was messed up, maybe your whole entire chassis would be ungrounded, but generally you can trust that the chassis is grounded well, and that's the reason why.
Why is that extra ground wire there?
So I was kind of trying to say, I think they've grounded the negative on the chassis, but I think this ground is probably going to go over to like the engine, or, you know, a lot of times they'll have multiples. Sometimes they'll ground the engine, sometimes they'll ground the transmission. I've seen where they ground the hood. I've seen where they'll run one to the body and then one to the frame if it's a truck. You know, so sometimes there's multiple, but anything that's shiny and metal should all be grounded, just so that way we don't have to run more wires than we need to. They can share the ground. So it's kind of interesting. And then we're just really summarizing that when we talk about those AC to DC, I want to give you a term: three-phase motors or alternators. Three phases, right? 1, 2, 3. So if you hear the term three-phase, don't freak out. It's just, that's kind of normal for AC. We typically use, if it's AC on a car having to do with hybrid or EV, it's probably three phases. It just means there's 1, 2, 3 wires, and each of the wire is at a certain phase in its cycle, and they're all offset by a third. So if you were to look at the clock or degrees, you'd have like zeros up here, and then 360 be a full circle. So it's going to be 0, 120, 240, 0, 120, 240, right? So they're evenly split, and they're all making these waveforms right here, but there's going to be 3 of them, and they're all going to be like offset a little. It's a little weird to explain, but just, it's not really a big deal other than understand your alternator makes 3 phases of electricity, and you don't really care because it sends it into a regulator rectifier, which makes it into DC. And as far as you know, we just test the alternator for DC. But back in the day, they used to have the alternator making AC, and then 3 wires would leave and go to a different box that was the regulator rectifier, and that would make it into DC. So if you had a car that didn't charge, you'd be like, is it the alternator or is it the regulator and rectifier? And you'd have to diagnose those two. Part of the reason I've backed way off on that is because now it's all one. So if you go to test your alternator and there's no DC coming out, who cares if it's on your AC side or your DC side? The alternator comes with both of these parts. So like, really, who cares? Unless, of course, you're going to like have some old cool car, or you're going to try to like replace a regulator rectifier on your alternator rather than a whole alternator, but good luck finding one. See what I mean? You can't go to the parts store and be like, hey, let me have this regulator rectifier. They'll be like, no, we got the whole alternator. Boom, there you go. Right, so things have changed. Cool. And that was pretty much the main summary. We'll do a little bit with AC for sensors sometimes, and other than that, really not a whole lot. All right, so how you guys feeling now? I think I'm pretty happy with where we're at. So.